Hi, welcome to Causal Inference 2, the sequel to Causal Inference 1. In Causal Inference 1, we focused on the identification and estimation of a few basic estimands, namely average treatment effects or effects of treatment on the treated. So, throughout almost all of Causal Inference 1, we assumed that 1. Treatment assignment was unconfounded given measured covariates. 2. Each study participant could be exposed to either the control condition or the treatment condition with positive probability. And 3, we made the stable unit treatment value assumption. At the end, we examined attempts to assess the plausibility of the unconfoundedness assumption and the extent to which the unconfoundedness assumption could be violated without reversing the conclusions of a study. Now, going forward, there are a number of interesting and important questions that scientists would like to address that require additional considerations. First, how does the cause produce the effect? Presumably, the cause operates by activating intermediate pathways between it and the effect. Addressing this issue necessitates the formulation of new estimands and, to identify these, extensions of the unconfoundedness assumptions previously discussed. A second issue is how to compare different treatment regimens. For example, a researcher might wish to know if administering a treatment once a week is superior to administering the same treatment every other week. In a randomized study where the investigator can assign subjects to different regimens, this is straightforward. But in an observational study where the investigator compares participants who took treatment every week versus every other week, treatment status in any given week can depend on previous treatment status, how well the participant is reacting to previous treatments, and other characteristics of the participant. These matters are addressed in the literature on longitudinal causal inference. Again, new estimands and extensions of the unconfoundedness assumption are needed. Third issue. We have assumed each subject has a positive probability of receiving treatment or not. This doesn't cover the case of experiments in which a subject's assignment depends on a cutoff score that he or she may exceed or not exceed. As an example, consider the case where a researcher wants to know the effect of a remedial reading program for school-age children on subsequent reading ability. While the best way to study this would be to randomly assign children to either receive or not receive the program, suppose the researcher can only conduct or has access to the study in which all children below the cutoff are assigned to the remedial reading program, and all children above are not assigned to the program. This might occur if the investigator who conducted the study was prohibited on ethical grounds from denying access to the program for children below the cutoff. This setup has come to be called the regression discontinuity design. Fourth, the SUDFA assumption, remember that stable unit treatment value assumption, is violated when there are multiple versions of the treatment and or interference amongst units. For example, if an aspirin is administered in gel or capsule form and the dosage differs in the different forms, or if the effect of a given dosage depends on the form, these are multiple versions of the treatment. Intuitively, this needs to be taken into account in order to achieve valid inferences. Interference amongst units occurs when outcome of unit I is affected not only by I's treatment assignment, but by the treatment assignment of other units, column I prime. Examples are common when outcomes may depend on social interactions among units, as in the transmission of infectious diseases, and when individual behaviors are influenced by other individuals. Fifth, one might ask if it is sometimes possible to identify and estimate treatment effects when it is not possible to observe all confounders. To that end, economists long ago proposed a clever and intuitive idea of exploiting longitudinal and clustered study designs in conjunction with modeling assumptions to neutralize the effects of the unobserved confounders. These give rise to so-called fixed effects regression models. Given the substantial use of these models in the social sciences, we examine them more carefully. Using the literature on longitudinal causal inference, we give conditions under which coefficients of the fixed effects models admit an interpretation as a treatment effect. Unfortunately, the conditions are usually very unrealistic. For the clustered case, in order that coefficients admit an interpretation as an effect, it is necessary to assume no interference among units. Again, often unreasonable for clusters sharing a common fixed effect. So, researchers typically have some idea of how the cause produces the effect. The question is of both theoretical and practical interest. For example, in designing a new intervention, a researcher typically targets one or more intermediate outcomes through which the intervention presumably operates. He or she then wants to know whether the intervention affects the intermediate outcome and whether or not the intermediate outcome affects the response variable. To fix ideas, let's consider the following example from Paul Holland in 1988, who, was the first guy who formalized all this stuff. So, in his example, students are randomly assigned to receive encouragement, or not, so it's an encouragement study, to study for a forthcoming exam. The exam score is the outcome. Presumably, encouragement affects the amount of time studied, which in turn affects the test score. Okay, so what questions might an investigator wish to ask in this case? So first, does encouragement affect the test score? Because the study is randomized, this is straightforward. Suppose the average treatment effect is positive. Yet, this does not indicate how this occurs. Perhaps it occurs because when encouraged, subjects put in more study time and learn the material better, thereby producing a better result. Perhaps that's not the case. Subjects put in more time when encouraged, but this doesn't produce a better result, as might occur if increased study time is not needed to produce a good result. But maybe encouragement improves focus during study time. Similarly, if it's focus that matters and encouragement increases focus, then the treatment effect should be positive even if encouragement does not increase study time. It seems there are many possibilities and many questions one might ask, including a number we have yet to even mention. So these types of questions are not new, and scientists have addressed these for many years using tools from econometrics, that's simultaneous equations models, and psychology, the more general structural equation models. Unlike the example above, these models were typically used in conjunction with observational studies, and many more variables than the three above were considered. However, it suffices to consider a simple example with one mediator to illustrate the issues involved in using these types of models. So, in the following treatment, I'll follow Holland, who first carefully studied the use of these models for causal inference using the potential outcomes framework. And to keep matters at their simplest, we shall, as in Holland, assume treatment is randomized and will ignore covariates X. In a linear structural equation model, one would model the three variables, treatment assignment Z, study time M, M for mediator, and test score Y, Y for outcome, using a two-equation model. So the first equation is the equation for the mediator, and the second equation is the equation for the outcome Y, and you'll notice that it involves both Z, the treatment, and M, the mediator. Okay, and we'll make the usual assumptions to identify the model about the errors. So, now one of the things we can do is substitute the equation for M, you see, into the equation for Y, and that yields what economists call the reduced form equation, which I've written out below. It's just simple algebra, arithmetic. So, from the reduced form equation, and recalling that we are assuming treatment assignment is randomized, we can see that the difference in the expectations in the treatment and control group, and it's randomized, so we can see that those parameters, that sum of parameters, is the average treatment effect. Okay, so sometimes we call it the total effect in this context. So the total effect consists of the direct effect, which is gamma y of z on y, plus the so-called indirect effect, beta y beta m of z on y through m. You'll notice that I put direct effect in parentheses, and then called the indirect effect, so-called. We'll look at other ways to operationalize that nomenclature later. So similarly, due to randomization, the beta coefficient, beta m, is equal to the average effect of the treatment on the mediator. So the indirect effect may now be written as the product of the direct effect of m on y with the average effect of z on m. Now, it is useful to look more carefully at these effects. The direct effect, which is gamma y, so just a couple of lines of algebra, no big deal. So the first line is just what it is. The next line we try to put in some potential outcomes. And then in the third line we note that, well, because after all, treatment is randomized, we can take the z out. We see a problem pretty quickly. In general, the direct effect gamma y is not a causal parameter because it compares y0 under the condition that when treatment is not assigned, the outcome m0 is m, as compared with y1, that is when treatment is assigned, under the condition that m1 also equals m. But these are really two different conditions because if you think about the expectation, you're comparing two different subpopulations. A subpopulation when m1 is m with the subpopulation when m0 is m, and those are two distinct subpopulations in general. They're not distinct, you can see below, if encouragement doesn't affect study time. Okay, but in general, if study time is affected, then those are two different conditions, two different subpopulations. So we need to compare under the same condition, or same subpopulations. So basically, that happens when either treatment doesn't affect the outcome, that is the intermediate outcome here, or you see also from the previous equation that if the mediators, if the mediator mi0 is independent of y0, the mediator mi1 is independent of y1, then you see you can take that out. You just look back at the equation and we'll have the expected value of y1 given m1 is the expected value of y1, similarly with y0. In a similar way, you can do this for yourself. The direct effect of m on y, which is beta y, that's not a causal parameter either for the same reasons. Okay, so what have we learned? In short, in a randomized study, or in an observational study where unconfoundedness holds conditional and covariates, if you go ahead and you condition on an intermediate outcome, in general, this yields estimands that no longer warrant a causal interpretation. Rosenbaum pointed this out in an article in 1984. It doesn't mean that such estimands are uninterpretable or not worthy of interest, but in order for them to warrant the causal interpretation usually given, additional conditions must hold. Now, in the next lesson, we're going to reformalize this and develop potential outcomes notation for the setup above, and give identification conditions under which parameters such as those above actually do warrant a causal interpretation. Well, having given those conditions, an investigator that may then decide whether or not these conditions seem reasonable for his or her application, and we'll also have some discussion of that ourselves. In this lesson, we're going to reframe the problem of mediation using potential outcomes. Following Holland and Robbins in Greenland, we defined several estimands of possible interest. As in the previous lesson, we assume treatment assignment Z is binary, but the results can be generalized to the case where it's not. At this point, we won't place any restrictions on the mediator M or the outcome Y. It'll prove convenient, even if it's redundant, to rewrite the potential outcomes yi0 and y1 as yi0, mi0, and y1, mi1, respectively, where mi0 is the value that unit I would take when not assigned to treatment, and mi1 the value if assigned to treatment. So we'll then define the unit effects of z on m and y as mi1 minus mi0, and yi1 mi1 minus y0 mi0 respectively. It's a lot to say. The unit effect of z on y is sometimes called a total unit effect. It's the outcome when unit I is treated and responds to treatment with the intermediate outcome value MI1 versus the outcome when I is not treated and responds with the intermediate outcome MI0. The unit effect can be viewed as operating through two channels. Treatment may affect M, which is MI0 is not equal to MI1, and this may in turn affect the outcome Y. And two, even if there is no effect on the mediator, that doesn't imply that the outcomes will be the same under treatment and control because Z may affect Y directly, meaning through channels other than M. In order to separate these two kinds of channels, we'll consider a hypothetical study with potential outcomes Y sub I ZM. Okay, so you'll see that's new. And Z can be 0 or 1, treatment or control, and M can take all possible values in the range of the random variable M. So with this new potential outcome, we can define several kinds of new effects. First, we can define unit effects. Okay, so where we compare Y under Z and M with Y under Z star and M star. In the literature on mediation, controlled direct effects of Z on Y, YIZM minus YZ star M, are commonly considered, but effects where Z is held at a value and M is varied, which may be called controlled direct effects of M on Y, these aren't commonly considered. If I average the unit effects, that leads to an average controlled effect, so CDE, controlled direct effect, or average controlled effects conditional on X, okay? So you can see that formula just takes the expectation within covariate level X of those two comparisons. So now, far more attention has been given in the literature to decomposing the total effect into so-called direct and indirect components, so now you see why we use that notation. If you look at the decomposition above, on the first line there's a decomposition of the total unit effect into a unit total indirect effect with treatment Z equals 1, so Z equals 1 is held there, and we're comparing the MI1 and the MI0. And then it's plus a unit pure direct effect of treatment at the mediator value MI0 when Z is 0. So you see that little decomposition. Okay, and in the second equality, the total unit effect is decomposed into a total direct effect and a pure indirect effect when Z is 0. Okay, so those are two different decompositions of the same thing, the total effect. The terminology above is due to Robbins and Greenland, but one often simply sees reference to so-called natural direct and indirect effects following Pearl. Now, Pearl just renamed the effects, but didn't change the definitions of these. In the following, where it's not necessary to distinguish between pure and total direct and indirect effects, I'm just simply going to refer to these guys as direct and indirect effects. Now, the two decompositions will generally give different values for the direct and indirect components, of course, unless additivity or no interaction occurs. And that's the no interaction condition right there. So it doesn't matter what value of M you're at. Okay, now Robbins points out that additivity is unlikely to hold in most applications. But a special case where additivity holds is when the unit direct effect is 0. Also, in that case, Z is an instrumental variable, as it affects the outcome only through M. And we'll have more on instrumental variables later. From this decomposition that we just saw, we can easily define average direct and indirect effects. For example, using the first decomposition, we get these two kinds of effects, or conditional on X. So the second one would be the direct effect and the average direct effect, and the first one would be the average indirect effect. Before we take up the identification conditions for the new estimands defined above, it's important to note that if the new potential outcomes are not well defined in the first place, it's meaningless to consider such estimands. Some dogmatic issues have been taken about this in the literature. I don't intend to take a dogmatic stance, but it seems to me there will be contexts in which it's reasonable to consider such random variables and contexts where it's not. So, for example, consider the encouragement study in the previous lesson. Subject I is assigned to receive encouragement or not, and they then choose how much time to study under each condition, mi0 or mi1. Okay? Now, in that case, to consider outcomes y, I, z, m, the investigator must at least be able to imagine the situation in which each subject might have studied m hours. That doesn't mean that the investigator must be able to design and or implement a study in which it's possible to assign units to receive that particular combination, although when this is the case, the resolution of this issue is more clear-cut, and there are some cases where that might be. Now, that said, an investigator might argue that his experiment did not manipulate the amount of time studied. And as it is not possible to force students to study little m hours, consideration of outcomes y, z, m is irrelevant, at least in a practical if not theoretical sense. As a second example, suppose that an investigator wants to study the effect of education on earnings as mediated through occupational choice. So let's zi equals 0 if at age 30 the respondent has less than a college education, and let zi be 1 otherwise. All right, and let's let the intermediate outcome denote the occupation at age 31. And let's let m star denote physician, and let's let y denote earnings at age 32. Okay, so clearly the outcome y0 m star, the earnings of a physician with less than a college degree, is not possible. It doesn't make sense to consider such a thing. Average direct and indirect effects have received much more attention in the literature than the average controlled direct effects. One reason is that the average direct and indirect effects indicate how the treatment or treatment assignment operates in the population to which the units belong. Large values of indirect effects indicate the mediator is a significant channel through which z operates. Small values suggest that either z doesn't substantially impact the mediator and or that the mediator doesn't substantially impact the outcome. In the former case, an investigator might look for a treatment that more effectively targets the mediator. If the effect on the mediator is substantively significant, suggesting the mediator does not impact the outcome substantially, the investigator might wish to rethink the experiment and try a different treatment aimed at a different channel. For a more extended discussion, you should see the encyclopedic book on mediation by Vanderweel. Now, it's also been argued that the average direct and indirect effects are of more fundamental scientific significance because they indicate how the treatment operates through the mediator, in contrast to the controlled direct effects, which fix the value of the mediator for all subjects. So while this is true of the controlled direct effects of treatment, that is not the case for the controlled direct effects of the mediator. These controlled direct effects are also the building blocks of the average direct and indirect effects, and in theoretical scientific context, it may be of more fundamental interest to know the effect of a mediator when its values are controlled than to know the effect of a treatment through mixtures of the mediating variables. At a practical level, for outcomes that measure beneficial quantities, if it were possible to manipulate both z and m, one would want to know how the controlled direct effects vary with z and m, also the value of its expectation that would yield maximum overall benefit. Economists often consider variables z, which are hypothesized to affect y only indirectly through a mediator of interest m. Here, while the mediator does not behave as if randomly assigned, z may have been randomly assigned or behave as if randomly assigned. In this case, the controlled direct effect is of interest, but the indirect effect itself is not. Z is just a tool to ascertain the effect of m when the relationship between m and y is confounded. So there should be a lot of more interest, I think, in controlled direct effects in the literature than there actually is. In the next lesson, we consider identification conditions for the effects defined in this lesson. So, in this lesson, we'll consider identification of the controlled average direct and indirect effects. Make sure that if you need to, you go back and look at the previous lesson if it's not fresh in your mind. So, with that, let omega sub m denote the range of m. So in a randomized study or an observational study with measured confounders x, we have the following condition hold, which should be pretty familiar. It's just the only new part is these new potential outcomes. So then if we look at the conditional expectation, the regular regression function, so we can write it. So if you see a yi, but you see a little z and you see a little m, then you're seeing a potential outcome y zm. Okay, now in the last line we take out the z because we can do so because of the randomization above. So there's just a little bit of simple arithmetic to get down to there. But now, okay, let's use what we just figured out. And what would happen if we tried to estimate the average direct effect using the difference in the conditional expectations? As we saw when we conditioned on an intermediate outcome, that generally led to a non-causal comparison. So again, we're going to look at this guy and we see, oh, okay, now I have the expected value of y1m, but I have when m1 is m, and I have the expected value of y0m when m0 is m. So you can really see clearly that that's a non-causal comparison from before and also now with this new potential outcomes defined, 1m and 0m. Okay? So we can really see it now. But the other thing you can see is that from that, what do you need to have happen? You need to be able to take the m out. So if we were to assume that the potential outcomes are independent, y little zm is independent of mi, z, same z, given x, or either one of those conditions, or y zm is independent of mi given x and z is z, which of course tells us we're seeing an miz. If we can do that, then what will happen is we'll be able to take out the m at the end, and we'll get that the expected value of y little zm given x, okay, turns out to be equal to the conditional expectation. So in other words, the conditional expectation will estimate the estimand that we want, or the conditional expectation is the estimand that we want in this case. Okay, now the conditions above do not suffice to identify the average direct and indirect effects, as pointed out by Robbins, for example, except in the special case when additivity holds. So we've done the control direct effects, but we're going to need a little more to get the average direct and indirect effects. Now, in this special case when additivity holds, the control direct effects and the average direct indirect effects, they're the same, so it doesn't matter. But in general, when that's not the case, it will matter. So we're going to need a little more. If additivity doesn't hold, see, we need to identify the expected value of the outcome y when z takes on the value little z, when it's set to z. But we're looking at the value of the mediator at z star. Z star could be z, which, okay, but we're also thinking of the case where z star is not equal to 0. So, for example, z might be 0, no treatment, but then we want to know the outcome, the mediator, when z star is 1 under treatment. If z is actually equal to z star, no problem. But if it's not, we're going to need to make some more assumptions, or at least a little bit more. It's not hard to see what's needed, okay, because you can just look at this. You want to get the expectation. You need to get the expectation of yz, little z, when actually the mediator is set at the value z star, which may be different. If you use iterated expectations, we'll get this when, so I'm just iterating over the, miz star given x, okay, and then if miz star is m, then I'm seeing a yzm, okay? And so what I need to make happen now is that expected value of yzm, given that the mediator is set at m, but the different value, mediator under the different condition, I need that to become equal to the expectation of the potential outcome given x, okay? And if I have that the following condition, okay, then I'll get that. Now you'll notice that this condition, before the condition for the controlled effects was just miz, yiz, m, and miz. Z was equal to z star. Now we have to assume that it's also true for the case where z is not equal to z star. And then if I can do that, then all we need to do is average this over the distribution of the mediator when it's at the condition z star. Okay? But by virtue of our randomization type assumption, this is just the conditional distribution of m given z is z star with x equal x. I know it's a lot to say in words, but just try to go through and do the algebra yourself and follow the words. It'll be I think, clear to you if you do that. Okay, so that was a lot. Now those identification conditions can be weakened somewhat. In this paper by Imai et al., they discuss some bunch of weaker conditions given by other authors. But in most studies where the conditions above would not be substantively reasonable, that would also be true for the weaker conditions. So for that reason, the comments below, which apply to these conditions, which apply to the conditions that I've just presented, they'll apply with almost equal force under these weakened conditions, okay, which I'm not presenting. But in that vein, it's important to point out that neither the condition below nor the condition that we used already follow. These are the conditions we assume to get these guys out, that neither of these conditions follow in either a randomized study or an observational study with confounders x, okay? So you can't just say I did a randomized study, or I'm assuming, that I have the confounders x for the treatment assignment, and that once I condition on those confounders, I have the equivalent of a randomized study. I mean, that's not good enough. People behave as if, or at least some people do, as if, I did a randomized study, now I can say whatever I want. Not about mediation. Not so. Okay? So the conditions that we've seen essentially state that values of the mediator under the treatment or control condition act as if they're randomly assigned within values of the pretreatment covariates. But this just isn't plausible in many contexts. For example, let's look at the randomized encouragement study with time studied as a mediator. So our condition states that the potential outcomes yi, 1m, for encouraged subjects are independent of the amount of time actually studied, given covariates. Well, certainly students who are not as bright and would therefore have lower test scores might choose to study more than the brighter students, so it seems unlikely that this kind of condition would hold unconditionally. Okay, now, possibly if you had measured covariates such as IQ, motivation, etc., such an assumption might be more credible, especially if the time between the measurement of the covariates and the test score was relatively short. And apropos of that, let's look at a different kind of randomized study. Let's suppose that then there's an actual study, a randomized study in which unemployed participants are assigned to a control group receiving no training, or a treatment group in which job search skills, such as resume writing, presentation of self, information on where jobs are located, are taught. The mediator is then a measure of job search activity, and the outcome is employment status. Now, given the training status, might we expect job search activity to behave as if randomized? Remember, that's the mediator. If so, there are no potentially confounding variables that affect both job search activity and employment status. This seems completely unreasonable. A potential confounder that comes to mind immediately is your confidence, as we would expect confidence to affect both the quality of job search and the likelihood of employment. So, an investigator might therefore try to include a measure of confidence in a vector of covariates x. But x, remember, includes only pretreatment variables, and pretreatment confidence is likely to be changed by treatment. Let's try to see where we can get. As the study is randomized, this is what the investigator is going to assume. Okay, now that's perfectly reasonable, that first line. And to take into consideration the post-treatment confounding by C, the confidence measure, he makes the following assumption, that the potential outcomes are independent of the intermediate outcomes, Z, given, values of the confidence. Now, if you look at the conditional expectation function under the previous line, you'll see that what happens is we'll get that the conditional expectation is equal to the expectation of the potential outcome conditioned on the value C when treatment is assigned to value little z. So then when you try to compare the z equals 1s with the z equals 0, treatment and not treatment, you'll see that you're comparing the potential outcomes 1m when C1 is C with the potential outcome 0m when C0 is C. And those are in general two different groups of participants and is not a causal comparison. So we're back to square one. Okay, so basically conditions established to study mediation don't allow for post-treatment confounders. And since this is quite common, this suggests that mediation analyses relying on the kinds of assumptions we've made will often be of limited value in practice. So now, don't want to be completely pessimistic. That said, statistical researchers have done a great service to the scientific community by making explicit the types of conditions upon which inferences about mediation actually depend, and also by developing sensitivity analyses, which I'll get to, which researchers can use to assess the impact of deviations from assumptions upon the substantive conclusions. So in the next lesson, actually next module, I'll take up estimation of mediated effects and sensitivity analyses for mediation. Now we're going to take up estimation of mediated effects. So if you haven't reviewed the previous few lessons, go ahead and do so now so that make sure we're all on the same page. Now the estimation is straightforward when you can use off-the-shelf software in conjunction with models. And so the most common case, we've already looked at it a bit, is the linear structural equation models with continuous outcomes m and y, extended here to allow for the inclusion of covariates x, and also, because we can do it pretty simply, interaction between the mediator and the treatment. I'm going to begin with a model for the potential outcomes and compare it to the model for the observed outcomes. You should be familiar with this strategy by now. So for z equals 0, no treatment, and 1, treatment. And for all m that you can get in the range of m, here's the model in terms of potential outcomes. Below, one equation for m and the next equation for z. And we'll make the usual kinds of assumptions on the errors with the potential outcomes that allow us to identify the model parameters and equate them with the average treatment effects and those kinds of things that we're interested in estimating. Okay, so as I say, the model parameters are denoted with the superscript c to indicate these are the parameters of the model for the potential outcomes. And when we get to the model for the observed data, the c's will come off. Now I'm going to use the model for the second equation for the outcome and define the controlled direct effects. Okay, so you can see this is just very straightforward algebra. And of course, the errors have zero mean conditioned on x. We've assumed that, right? All right, so you get this term, this alpha y, which has to do with the difference between treatments, and you get this beta y, which has to do with the difference between the mediators, and then you get this interaction term, the delta y for the interaction. All right, let's move forward. With z and m interacting, the direct and indirect effects depend on which of the two previously discussed decompositions of the total effect that we use. Remember, when they don't interact, when we have additivity, the two decompositions give the same result. We saw that earlier. In any case, the effects may be derived using this equation for the potential outcome, yiz. So that's just when you take z, when you set z, and then you set z star to be either z or not z, then the actual value of the mediator at that point. So now we get this equation. You can just do the algebra. And under the conditions for the identification of average direct and indirect effects that we gave previously, we get the following two results below. Okay. And of course, we need this expectation of the errors to be 0. We've seen that kind of thing before. Using these identification conditions, analogous parameters in the observed data model, okay, you see that's the same sort of model, but with the c's taken off, and a different assumption about the errors because we're conditioning on z as well. These are the sort of the regression errors. And anyways, when we have the identification conditions holding, the model parameters in the observed data model and the potential outcomes model are the same, so that we can use the observed data model to estimate the direct and indirect effects and controlled direct effects, of course, as well, which require actually somewhat weaker conditions. We can estimate all these guys using the coefficients in the observed data model, the estimated observed data model. Okay. For the remainder of the lesson, I'm going to assume that the observations are independently identically distributed. So then the model, the observed data model, I'm going to estimate by applying ordinary least squares regression to each equation. And then the delta method can be used to obtain standard errors for the estimated effects. If you're not familiar with the delta method, look at an elementary sort of probability or statistical inference text, one that, of course, assumes you've had calculus at least. Now, if the mediator is continuous, but the outcome y is binary, you probably wouldn't want to use a structural equation model for a continuous outcome y. So it seems natural to use logistic regression model or a probit model to estimate the outcome probabilities. Okay, so remember we're focusing on the use of off-the-shelf software to estimate direct and indirect effects. So if you use the logistic model with the mediator following a normal distribution, least conditional, then this paper by Vanderweel and Van Steelen give formula in terms of model parameters for average direct and indirect effects. But the effects are now defined in terms of odds ratios, which is kind of a common thing that's often done. Some people don't like it, and some people think it's fine. Similarly, when the mediator is conditionally normally distributed with constant variance and the outcome is a survival time modeled using the accelerated failure time model, which is a special model, Vanderweel gives formula in terms of model parameters for differences in logged outcome means. Okay, that said, the difference cannot be expressed as the difference of the unit effects for the outcome y or some transformation of y. Now, so much for use of off-the-shelf software for estimating these average direct and indirect effects. So more generally, Hong has proposed a general method for estimating average direct and indirect effects based on an extension of the weighting approach we saw in part 1. Remember the inverse probability treatment weighting. Okay, now the method does not require modeling the outcome y, which is a point Hong emphasizes, but it does require modeling the mediator m and the treatment assignment process. So, Hong shows that under the identification assumptions given in the previous lesson, you get this for the expected value of y of little z, the potential outcome z, and then when m takes on the value that it would take on if the treatment assignment variable were set to z star. Okay, so now another approach that doesn't use off-the-shelf software, Imai et al. Proposed several approaches using simulation. Both of their approaches require modeling both the outcome and the mediator. And one of these approaches uses a sampling distribution of the model coefficients. The other approach, which can be used more generally, begins by drawing bootstrap samples, of the original data. Now, for each bootstrap sample, the models for the outcome and the mediator are then fit. Then, for each unit I, and for each possible value z of the treatment, k values of the mediator are simulated under the model. And these simulated models, the S up there is for simulated, the simulated values of the intermediate outcome, the mediator, are used in turn to simulate corresponding outcome values, as you can see there. Then the outcome values for the units are averaged, and then they're averaged over the units. And that gives estimated average direct and indirect effects for bootstrap sample little l. The estimates from the L bootstrap samples may then be used to compute means, confidence intervals, etc. Okay, so far we've discussed identification and estimation of various kinds of mediated effects, average direct and indirect effects, controlled direct effects. Okay, now you'll recall from way back when, the module on identification, you'll recall that these mediation analyses require rather heroic assumptions, and therefore it's useful to try to assess what happens if these assumptions aren't met. Now I'm going to talk a bit about sensitivity analyses for mediation. And hopefully you'll recall that we discussed that a little bit in Causal Inference 1. Okay, because if you recall the discussion there, then what we're going to do here is just a very straightforward extension of that. It involves just sticking in the mediator. Okay, so I'm going to omit the subscript I in this lesson, and I'm going to review the approach in part 1. Okay, so you have observed confounders X, and you have an unobserved confounder U, and you have treatment assignment Z, and you have your outcome. So it's just like in Causal Inference 1. Now, the goal is to estimate the average treatment effect at the value X. Yeah, it could be something else, but you'll get the idea here. Now, the assumption is the treatment assignment is unconfounded given X and the unobserved covariate U, but the investigator assumes unconfoundedness given X. So now the bias from ignoring U, it's pretty simple to write out, is what the actual difference in expectations in the treatment group and the control group conditioned on X. Okay, because if we didn't have U in the way, that would be the average treatment effect at X, but it's not because of the U. And then we have to difference out what we really want, which is the average treatment effect. So you can see that that's just a straightforward expression for bias. Now we're going to rewrite it a little bit. Now we're going to have this unobserved continuous confounder U. The bias at X can be written as follows. You can just do that yourself. It's pretty simple. If you look at the first expression, that's just the expected value of Y given X and Z equals 1 minus the expected value of Y 1 given X. And then the second expression is the same for in the control group. You can write that out for yourself using the previous definition of bias. Now, if I integrate the bias over the distribution of X, then I can get the unconditional bias. But we're not going to worry about that right now. But I mean, that's how you would do it. Now, we expressed the bias, and so the utility of a sensitivity analysis will hinge on whether or not the investigator can make some reasonable assumptions about the unknowns in the previous equation. So, here's what van der Waal and Ara assume about this. So they make this assumption that the expected value of Y given X and Z equals 1 and U is at some value U versus the same thing when U takes on some different value, that those guys are equal in the treatment group and the control group, you see. And I'm going to come back to that momentarily. Now, then they say in the special case where U is binary, the integral, of course, is replaced with a sum, and a little arithmetic gives you this nice little expression. And then a sensitivity analysis would then proceed under various assumptions about the magnitude of these two components. And you can obtain similar results for risk ratios, but I want you to see something, and that's the assumption that they've made that those two guys are equal in the treatment group and the control group. That's a pretty strong assumption. So rearranging and using the unconfoundedness assumption will give you the following. So what we're seeing is the expected, the average treatment effect at X and the value U is equal to the average treatment effect at the value X and U equals U prime. And a sufficient condition for this to hold is that the difference between Y1 and Y0 is independent of U given X. So given the covariates X, the difference in the potential outcomes does not depend on the unobserved confounder. Now, this is certainly more credible than assuming the potential outcomes are independent of U, given the unobserved confounders, but the condition still seems quite strong, and an investigator who is unwilling to make this stronger assumption may also generally be unwilling to make the weaker assumption above. A minor modification of the results above leads immediately to sensitivity analyses for the controlled direct effects. To that end, suppose the previous assumptions we made to identify these effects hold once we add U to the conditioning set. So now we just go through and essentially now we have a mediator in there. And the bias can now be written, okay, and you'll see that it's essentially the same expression, except now we also have the mediator, M, in there. As before, if you integrate over the distribution of X, you'll get the unconditional. Now, van der Waal considers the case of the controlled direct effects. And then if we assume the same kind of assumption, you'll see that Z equals 1 in the top and Z equals 0 in the bottom. So we're assuming an equality between the treatment groups and the control groups. Then in the special case where U is binary, the integral again is replaced with a sum, and we get a nice tidy little expression for the bias. parallels the expression we had previously, except now m's in there as well. And as before, sensitivity analysis would then proceed under varying assumptions about the magnitude of these two components. Now, as before, we can rewrite that condition that's assumed in the following sort of way. We see that we're making, again, a pretty strong assumption in order to do the sensitivity analysis, an assumption we may not be comfortable with. Under additional types of conditions given for the identification of average direct and indirect effects, the bias due to ignoring U for these quantities can also be obtained. And I refer the reader to the book by Vanderweel that's previously been mentioned, the sort of encyclopedic book on mediation. And I should also mention that for the case of linear models, Imai et al. Have some nice results. In a randomized study, where U is not a confounder for the relationship between outcomes and treatment assignment Z, the confounder U is needed to make the relationship between the potential outcomes YZM and the mediator M conditionally unconfounded. A crucial point is that in the approaches above, U is either a pretreatment covariate or a post-treatment variable not affected by Z. The more likely case of confounding by post-treatment variables affected by Z is not covered above. All right, so now I'm going to turn to different approaches to dealing with intermediate outcomes, namely instrumental variables and principal stratification. Okay, so now we're going to talk about instrumental variables when the treatment variable is continuous, which is a setup you often find in economics. A special case of mediation occurs when the treatment assignment variable Z affects the outcome only through the mediator M, i.e., Z does not directly affect the outcome Y. And we formalized that notion before, remember? Now, in a randomized double-blinded encouragement study, such an assumption can be reasonable. In randomized studies where subjects know which treatment group they belong to, such an assumption is less likely to hold. For example, if Z denotes assignment to a job training program or a control group, and M denotes whether or not the treatment is taken, a subject assigned to treatment who does not take up treatment may feel demoralized because he or she didn't take up the treatment and therefore feel more depressed than he or she would feel had she been assigned to the control group, which would get you a direct effect. Now, natural experiments are observational studies where an event that is essentially randomized is used to assign units to a treatment or a control group, and the assignment is presumed to affect an intermediate outcome that in turn affects the outcome Y. So in analyses of data from natural experiments, it's often assumed that assignment does not directly affect the outcome. So, as an example, Angrist, Imbens, and Rubin used the draft lottery as an instrument to study the effect of service on excess civilian mortality. Now, under the assumption, which is sometimes called the exclusion restriction, we called it no direct effect, the exclusion restriction below that Z affects the response only through the intermediate outcome M, the control direct effects and the natural direct effects are zero. I mean, that's fairly straightforward. And it's easy to see that the average indirect effects do not depend upon the decomposition that you use. Remember, in general, we had two different decompositions, which led to two different indirect effects. And the average indirect effect is now equal to the total effect, of course, because there's no direct effect. So total is equal to direct plus indirect. When there's no direct, total is equal to indirect. Now, if we make the additional assumption, okay, and this is the kind of thing we've been assuming anyways, when we did direct and indirect effects, and under which the total effect was identified, remember, the average indirect effect is clearly identified because it's the total. So importantly, if the exclusion restriction holds, that is, the direct effect is zero, it's not necessary, as it was before, to make additional assumptions about unconfoundedness of mediator-outcome relationships that are often unreasonable to identify this effect. So at least we can get our hands on the indirect effect without making a whole lot of assumptions other than the one above. Okay, and the one above in a randomized experiment, presuming that we think it's reasonable to define these kinds of potential outcomes, then that's pretty reasonable. However, It's often the case that such indirect effects are not of primary interest. In the examples above, scientific interest focuses on the controlled direct effects, where you're comparing different levels of M at a given Z. So what do those guys do? They capture the direct effect of the mediator on the outcome. But the exclusion restriction and the condition that there is a non-zero effect on the mediator don't suffice to identify these effects. So now we're going to look at some additional conditions under which these effects, okay, remember we're interested in the effect of the mediator on the outcome. So we're going to look at some conditions under which some such effects and related effects are identified. Okay, so let's start to formalize this. We'll say that Z is an instrument with respect to the outcome Y if Z has a non-zero effect on the mediator, given X. And here's our randomization assumption. And now we've made this exclusion restriction assumption. So we've got these three assumptions at this point. I want to say that there's a lot of literature in economics and statistics on instrumental variables, which are often called IVs, and this is a pretty active area. Now, Angrist, Imbens, and Rubin, in this article I've already talked about, and it's a great article, require also that an instrument satisfy a so-called monotonicity condition, which we'll get to. So what it says is that the value of the mediator outcome under treatment is greater than or equal to the value of the outcome under control. Now, I also want to say that in the econometrics literature, an instrument is often defined using notation for observed outcomes only, and instruments are used in other, sort of non-causal contexts as well. So if you're interested in all this stuff, there's a nice textbook by Green on econometrics that gives a nice introduction, and there's a review by Imbens that covers work at the interface of this subject with causal inference. Oftentimes one sees the following: since there is no direct effect, sometimes they just get rid of the Z and write the potential outcomes as YIM, because it depends on whatever you've set M to, if you can set M to or thought about. Okay, so now we're going to consider three prominent cases. Z is binary, like treatment or not, with M and Y continuous. Now, both Z and M are binary. And 3, Z is continuous and M is binary. These are the three cases we're going to really consider. Take some time to do so, but we'll take them all up. So I'm going to begin with the first case. And I'm going to use a linear model for the potential outcomes to illustrate, which that ought to be a pretty familiar model. We just essentially looked at it, but of course now we're going to have what? No direct effect of Z. Okay, you can see that in the second equation. And we've rewritten YI only with M, not with Z and M. Otherwise, can take out the interaction, and otherwise it's identical to what we saw a couple of lessons ago when we talked about estimating mediated effects. Okay, so the model, as I said, is just a special case in which the exclusion restriction is assumed of the linear model studied in Lesson 1 of the module. And the C superscript is causal model, and I'll remove the C when we talk about models for the observed data. Okay. All right, so here's our model. Okay, now we've assumed, remember we decided that an instrument ought to have, there should be some effect of treatment on the mediator. So under our assumptions, we have this beta M is the effect of the treatment on the mediator, the average effect. And we have this tau C, which is going to be the indirect effect, and it's equal to this product of these coefficients plus this error term. So we'd like it, think back to structural equations, we'd like it to be just the beta Y times the beta M. In order for that to be the case, we need this expectation of the errors to vanish, okay? All right, now, how would we get that to vanish? If we made this very strong constant effect assumption that the errors are equal for all M, then the ratio of the total over beta Y, which is a so-called IV estimand, would be the average controlled direct effect of M on Y for all X. Now, this constant effect assumption is really strong because it basically says that the error doesn't depend upon M at all. Sometimes this is referred to as the assumption of no treatment heterogeneity in economics. Now, you can also, of course, get this result when treatment effect heterogeneity is present just by assuming that expectation, that annoying expectation, is 0. Now, in a paper I wrote many years ago, I gave some conditions for this to hold. And there's other conditions in the literature like this. And the conditions are more general. You can also do this in the case where you do have direct effects. Okay. But the conditions are weaker than the condition previously studied in the mediation literature, that the mediator-outcome relationship is unconfounded given the covariates in treatment assignment. That's what we did assume. That's an assumption that we've made for identification, mediator effects, and I criticize that. But the assumption of constant effect, I showed that in that article, is neither stronger nor weaker than the unconfoundedness assumption above. In related conditions, you can also find in the econometrics literature. There's a nice text by Wooldridge. And economists have also studied IVs in the context of nonlinear, semi-parametric, and non-parametric models, much more fancy than what we've done. But I just wanted to get the basic ideas across. And if you're interested in these sorts of things, these sort of nonlinear, semi-parametric, non-parametric, you can look at the paper by Inference that I talked about before. I guess the one thing I do want to say is that we can weaken those assumptions, but that's still, I consider the assumption about the errors above. It's about the difference in errors as opposed to the absolute errors, because the YIZM in above can be written, I could write it in terms of errors, epsilon IZM. I still consider this to be pretty strong on the condition on the difference of the errors. It's weaker. You can show that it's more or less weaker, but it's still pretty strong. Okay, in the next lesson, I'm going to begin with case 2, where the instrument Z and the treatment M are both binary. And this is the case where Z denotes assignment to a treatment group or a control group, and M often indexes whether or not the assigned treatment was taken or not. Okay, and this is basically, if you refer to the subject of compliance, this is compliance, and it's going to lead us more generally to the subject of principal stratification. Okay. In the previous lesson, we studied the case where the instrument Z was binary and the intermediate outcome M was continuous. In this lesson, we're going to do something a little different. We're going to have M also be binary. Okay? And we're going to make the exclusion restriction assumption again. Remember, that's that when you have value M on the mediating variable, it doesn't matter if that comes from the treatment group or the control group, so that treatment itself operates through the mediator. Okay? And so that's going to allow us to write the extended version of the potential outcome, which depends on both Z and the outcome Mi of Z. We can just drop the Z because it really doesn't matter. For Z equals 0 and Z equals 1, it's the same. Okay? Now, the first thing we're going to do is introduce so-called moment-based estimation. And we're going to assume that treatment assignment is unconditionally unconfounded. And I've written down what that means below. All right, so that makes sense. And the other thing we're going to assume is that the average effect of the instrument on M is non-zero. In other words, the instrument does hit the mediator, have an effect on the mediator. All right, so that's what we're starting out with. Okay, now we're going to use the unconfoundedness assumption first to look at tau C, which is the overall effect, overall average treatment effect, or, it's called, sometimes we've called it the intent to treat estimand. It's also been called the total effect back there in some of the previous modules. Anyways, we should be familiar with that at this point. And so by the unconfoundedness assumption, we get this, okay? So using the exclusion restriction, we break down the total effect. And so it breaks down into the average treatment effect in these two subgroups. The subgroup where Mi0 is 0 and Mi1 is 1. In other words, one is doing what they're supposed to do under the treatment assignment, and the average treatment effect amongst the folks that do exactly the opposite of what they're supposed to do. And the other two, well, by the exclusion restriction, the Y1s minus the Y0s are 0, so they go away. So now one of the ways in which this has been studied is in the context of compliance. Okay? And so if you have an experiment where there's noncompliance and the MI denotes whether or not you receive the treatment, it's typical to assume that the probability that when assigned to the control group you take the treatment and when assigned to the treatment group you don't, we assume that that's 0. Okay, it's also called a monotonicity assumption or an assumption of so-called no defiers. Okay, now in this case, this is actually an identification condition, but it's quite reasonable in many cases. So when you have this identification condition, so the expected value, the average treatment effect of Z on M reduces to this probability that M0 is 0 and M1 is 1. So under the additional assumption that we made above, i.e. no defiers, we obtain the so-called IV, or instrumental variable estimand, which I've written below. And here, that takes on this special form of, and you can just see it from the arithmetic above, you can do that. Here, that's just the average treatment effect amongst the subpopulation of folks who basically do what they're supposed to do under the treatment assignment. In other words, when they're assigned to the control group, they don't get the treatment, and when they're assigned to the treatment, they take up the treatment. Okay? So usually, we're used to dealing with a lot of assumptions that are untestable, but the assumption that Z affects M is testable. Now, the estimand that we have is often called the complier average causal effect because we're looking at the special subpopulation with the M0 is 0 and the M1's 1. These are the folks that do what they're supposed to do. We can call them compliers. Okay? They are a latent subpopulation, and we can't really see the compliers, but, it's reasonable to call this subpopulation latent even, to call them compliers. So for this reason, we sometimes call this estimand the complier average causal effect, and it's sometimes also called the local average treatment effect. So now if we go ahead and assume the observations are independent and identically distributed, the IV estimand can be estimated using the sample averages. Okay, so I think that's pretty straightforward. All right, so that's the basics, very, very basics. So more generally, you might wish to think about variation in the causal average complier effect within levels of covariance X. Or, it may be this case that confoundedness, which we assumed above, may not hold unconditionally. You might need to condition on some covariates. Okay? So now, for the case where X is discrete, the sample means within covariate classes can be used. Okay? So you're just partitioning into covariate classes and doing the same thing. But of course, if X is continuous, or there are many, many levels of X, we're going to need to introduce some modeling assumptions. Standing back and looking at this case, I'm just going to start calling it case. It's been argued that for a given intervention Z, the policy relevant question is the overall effect, which is sometimes called the intent to treat or ITT estimate. I think I've used that before, of the intervention, not the effect for some subset of units who will comply with whatever assignment they're given. So, for example, if Z is a medical treatment that is to be taken in an unsupervised environment, say at home, the practical effectiveness of the treatment is the effect in the context in which the treatment is delivered. Furthermore, the case is not even the average effect for all those who would take up treatment if it were offered, as the experiment is not informative about units who take up treatment regardless of their assignment. In addition, even if you wanted to target the treatment towards the units who might benefit from being offered treatment, the compliers are a subpopulation that cannot be observed because we cannot observe both potential outcomes M0 and M1. These are some arguments against the utility of the case as an estimand in a real practical context. Okay? Now, on the other hand, people have argued that case is sometimes more broadly representative of the population. All right, so let's look at that. So when there are no defiers, the average treatment effect is a mixture of the average treatment effects among three subgroups: the compliers, the always takers, and the never takers. Units with M0 equals M1 equals 0. And the always takers, M0 equals M1 equals 1. So if the average treatment effect is the same for compliers and always takers, This gives the effective treatment on the treated. And if this extends also to the never takers, the complier average causal effect is also the average treatment effect. But of course, you'd have to make arguments for why that would be the case. All right, substantive arguments. And they'd really be tantamount to making assumptions, because you can't really know if it's true or not. That said, unfortunately, it's pretty common to see empirical work where the ATT or the ATE seems to be the parameter of substantive interest, but where the case is estimated and extrapolated without further argument or consideration to the parameter of interest. That is, you're estimating the case, and some folks that doing empirical work seem to forget that that's not the ATT or the ATE, which is what they're really interested in. So if the compliers are a large majority of the population, that kind of problem may be not too bad. But let's look at the Angrist-Imbens-Rubin paper, great paper, and the question of interest they start out with is the effect of military service on excess civilian mortality. And then we find out that the compliers are about 16% of the population. So they give you the complier average causal effect. Now, in this case, it might be reasonable to believe that never takers are unhealthier than compliers or always takers, and that the mortality rate would have been higher had it been possible to take into account the mortality of this subpopulation. So it applies clearly to that 16%, but how representative is that 16% of all the other folks? Now, to take confounders into consideration, unless these are discrete and with few levels, you can't proceed non-parametrically as we've been doing above. So now, let's suppose we have a random sample, and let's suppose that the unconfoundedness assumption holds conditional on x. So let's let this f of m of z equals m, y given x, denote the observable conditional distribution of the outcome y among subjects with the response m. Remember, m is binary now, as is z. Okay? So there are 4 such distributions. Okay? You can write them out. Now, if you use the monotonicity condition, which is m1 greater than or equal to m0, remember that's notifiers, okay? That implies that subjects with m0 equals 1 are always takers. And thus, if we see a z is 0 and an m0 is 1, we know we're seeing an always taker. So that's why I've relabeled that as fa for always taker and 0 for z equals 0 of y given x. So similarly, subjects with m1 equals 0 are never takers by the monotonicity. And fm1 equals 0 is, I've relabeled that fn1. That's the distribution of the never takers under treatment assignment to treatment. The remaining distributions, if I see an m0 equal to 0, so when you're assigned to the control group and I see that you actually don't take up the treatment, well, okay, you could be a complier. You could also be a never taker. So it's a mixture. Similarly, if I see that when you're assigned to take up treatment and you do take up treatment, I don't really know if you're a complier or whether you're an always taker. That distribution is a mixture of those guys. The always taker distributions under the control group, and that's when you're assigned not to have treatment, and the distribution of the never takers when assigned to have treatment, and the mixture probabilities, okay, and distributions, you can identify those guys in some instances under additional assumptions. So, as an example, suppose the outcome y is continuous and the mixture distributions are assumed to be mixtures of normals with these means. So mu c0 x would be conditional on x, the mean for the compliers under no treatment, the mean for the compliers under treatment, x, etc., etc. And we might assume a common variance sigma squared. And a thing that's been done in the literature is that the mixing probabilities follow multinomial logit model. And you can see there's only 2 of them there because the other one by default is the probability of being a never taker at covariance x. The assumption of a common variance you can relax, but it can create some difficulties. It's a general phenomenon. So an assumption that was commonly made in that kinds of analyses that I just described, is that the distributions in never takers are always the same for z equals 0 and z equals 1, which is basically a stochastic version of the exclusion restriction that we made in conjunction with the discussion of instrumental variables. But it is important to note that this assumption doesn't require the potential outcomes, y, zm, as when we studied mediation. They don't need to be well defined. So one of the earliest papers in this genre, a very nice paper, was written by Little and Yao in 1998 that appeared in the Journal of the American Statistical Association. Here, there are no always takers because you really can't access treatment outside of the treatment group. And so the analysis reduces a little bit. And that's a fairly common kind of thing in actual experiments. In the last lesson, we talked about a binary instrument, and then the treatment itself, which was the instrument causing treatment. The treatment itself was binary. And that led us to talk about the causal average complier effect, etc., etc. Now, principal stratification can be viewed as a generalization. Okay, you recall we were, with the causal average complier effect, we were looking at estimation within the latent subpopulation of compliers. So we can generalize this idea of estimation within latent subpopulations, now called principal strata. And these principal strata are defined by post-treatment potential outcomes, just as in the case of the case, and they lead to the estimation of so-called principal stratum effects. So you can see that what we're doing is we're estimating the response y under the difference between treatment and control, but in these latent subpopulations, and they're latent, of course, because we're going to see an M0 or we're going to see an M1, but we're certainly not going to see them both. And so we could do this like above, or we could do this conditional on covariates x, as in the second equation. So, as again, I want to mention that these effects do not require us to define potential outcomes yzm, which in some contexts is an advantage. In another context, it's just different. Going back to the previous lesson again, we looked at the special case in which the intermediate outcome M was indexed by whether or not a subject took up the assigned treatment or not. And then we used an exclusion restriction and a monotonicity condition to make up our case. And we saw that the ITT, which I'm writing on the left, we saw how that reduced to the product of the case with the complier probability. Okay? Now, more generally, you may want to relax these assumptions and allow M to have even more categories or to be continuous. Maybe also allow for the possibility that treatment assignment depends on covariates. You may not have unconfoundedness overall, but you may have unconfoundedness given covariates. Or you may just be interested in treatment effects that vary with covariates. Let me give you an example about principal stratification. Consider the following question. Does coronary bypass surgery improve a subject's quality of life? Okay, well, that seems to be a causal question. So we want to compare a subject's quality of life when he undergoes surgery with the quality of life when he or she foregoes surgery. You see, and there's an immediate problem. You can only ascertain the quality of life for subjects who survive. So let Z be 1 if the subject receives surgery, 0 otherwise, and let MI be 1 if I survives and 0 otherwise. So one solution is to simply define the quality of life as 0 for subjects who do not survive. This seems kind of arbitrary. So another solution is to compare the survivors who receive surgery with the survivors who did not receive surgery. But recall that if assignment to Z is randomized, this would give you the descriptive comparison, because I can take out the Z, but I can't take out the M. This is very similar to where we started the whole set of lessons on mediation. Anyways, unless we're willing, as in the case of mediation, to assume survival status M is independent of the potential outcomes YZM, or something weaker but still not very reasonable, we can't really make a causal comparison. However, if we confine our attention to those who survive under either condition, which seems to be the reasonable comparison in any case here, we obtain the estiman, the difference between treatment Y and control Y, given the group that would survive under surgery and also without surgery. This is a so-called survivor causal average effect. And for other examples where this is of interest and for some other estimates that fit into the principal stratification framework, there's a nice, very accessible paper by Page, Feller, Grindle, Miratrix, and Summers. As before, identifying effects within principal strata will require assumptions. Okay, so the monotonicity assumption is often made, and in many contexts it's reasonable. So, for example, if we're studying test outcomes, you might be willing to assume that a student studies more when encouraged to study than when not. Okay, this is an example where the mediator is continuous. Okay, an example that we used before. So more generally, in randomized studies where the treatment is designed to operate through a mediating variable, one might be willing to make some sort of monotonicity assumption. Similarly, in a study of fitness, a subject assigned to an exercise program or a diet may be more likely to exercise more or diet more than in the case where they had not been assigned. In some instances, it may also be reasonable to assume something like there is no effect on the outcome in strata where the intermediate outcome is unaffected by treatment. Now, in general, more assumptions are going to be required to identify causal effects within principal strata when m takes on more than two values. So, as an example, if m were to take three ordered values, 0, 1, and 2, we have three principal strata with m1 less than m0. Now, so we might go ahead and assume that's not possible. So that means that the probabilities in those principal strata are 0. Then if we assume monotonicity, we're going to end up with 5 of the 9 principal stratum probabilities being identified, but without at least one additional restriction, the remaining probabilities are not. In other words, monotonicity alone isn't going to get us identification of all the principal stratum probabilities for the case where m takes 3 ordered values. Okay. Now, furthermore, even if a restriction were imposed to get us identification of the principal strata probabilities, without further restrictions on the values of the principal strata effects, these would not be identified. So, for example, suppose we now knew the principal strata probabilities. Then, by the monotonicity condition, if you see that m1 is 0, that tells you that m0 must have been 0. So the principal stratum effect in this stratum is identified. And similarly, if you see that m0 is 2, that means m1 is 2. So that's the probability that m0 is 2. So the principal stratum effect is identified in this stratum. However, you can show that the remaining principal stratum effects are not identified without imposing further restrictions. Now, if m takes on more than 3 values, identification will require even stronger assumptions. So as before, for continuous outcomes, one might use some kind of parametric mixture model with covariates. So for some examples of how one might go about this, there's a paper by Jin and Rubin in 2008 in the Journal of the American Statistical Association. And also there's a paper by Jaffe, Small, and Xu in 2007 in Statistical Science. Both of these are pretty nice papers. All right, I'm going to switch topics now. I'm going to take up regression discontinuity designs, which are related to instrumental variables, as it turns out. So the regression discontinuity design arises when treatment depends on thresholding a continuous score. So that the reader may see the similarities and differences between this design and its analysis and the previous material on mediation, instrumental variables, and compliance, I will denote the score Zi, treatment Mi, and the outcome Yi. In the previous module, we discussed principal stratification. And now we want to move on to regression discontinuity, which appears here in the discussion because it has relationships to mediation and to instrumental variables, although they're not always obvious, or at least framed in that way. So now, regression discontinuity. These kinds of designs were pioneered by Thistlethwaite and Campbell, educational psychologists, nearly 60 years ago in an educational study, to evaluate the effect of receiving an award on subsequent outcomes, such as receiving scholarships. The key thing is that the receipt of an award was based solely on a test score, Z. Okay, so Thistlethwaite and Campbell reason that students just above the cutoff and students just below could be compared, and thus the effect of an award could be estimated at least right around the cutoff value Z0. So these kinds of assignment processes are not at all unusual. In medicine, where persons who have cholesterol levels above a certain number may be prescribed a pill. Similarly, a surgery may be performed only when the value of a critical indicator has been passed. In urban planning, only streets where one or more fatalities have occurred in the past year may see a change in the speed limit. So such designs are also popular in the social sciences and have been used and studied extensively, especially by econometricians. Readers who want to read about the applications in economics may wish to look at the review paper by Lee and Lemieux. And the Journal of Econometrics devoted a special issue to this topic in 2008, as did the Journal of Observational Studies in 2016. At first, it might seem odd that anything can be learned from a design where there is no overlap in scores between units receiving and not receiving treatments. So in Causal Inference 1, we focused on the unconfoundedness condition, noting that problems ensued when it was not possible to find observations in the treatment and control groups with similar values of the covariates or propensity score. So now the question is, what can we learn when the unconfoundedness condition holds, but the overlap assumption may not? So clearly, you cannot, at least without making lots of possibly unjustified assumptions, learn about treatment effects far away from the cutoff. So we'll focus on the neighborhood right around the cutoff. And the following exposition parallels the treatment in a paper by Hahn, Todd, and van der Klauw in 2001 in Econometrica. It's a very short paper. It's just a little note, but it's just such a nice, beautiful paper. It's really quite nice and so clear. So let me try to follow them. So the score, Zi, that's the score that has a cutoff Z naught. And so treatment M of Zi takes values 0 or 1. Is yi of mizi, which is, mizi is 0, it's 1. That's it. So the potential outcomes are yi 0 and yi 1. And the thing we want to estimate is the expected value of the treatment effect at the cutoff point Z0. Now, there's going to be two types of regression discontinuity designs of interest. The first is a so-called sharp design. If you're above the cutoff, or at the cutoff or above, you get treated. Otherwise, you don't get treated. And that's it. Now, in this design, clearly, the probability that you get treated obviously doesn't depend on the potential outcomes. It only depends upon the cutoff. So that the probability that you're treated is 1 given Z. So treatment is clearly unconfounded, right? Because the treatment is independent of the potential outcomes given Z. Okay, so above the threshold, there are no control units to compare with treated units, and below the cutoff, there are no treated units to compare with the control. So you have unconfoundedness, but you don't have overlap. Now, in a fuzzy design, assignment is probabilistic. So basically, the idea is that you're much more likely to get treated if you're above the cutoff than if you're below the cutoff. But there may be units slightly below the cutoff that end up getting treated anyways, and units slightly above the cutoff that don't get treated. It's a fuzzy design. So it's common to make so-called regression discontinuity assumption. So M minus is the limit of the probability of you being treated given Z. And so you're coming at Z from below. You're coming at Z naught from below. So this is a limit as you go towards Z naught from below. And M plus is a limit as you go to Z naught from above. And so you don't expect them to be the same. So M plus should be greater than M minus. And so that's the so-called regression discontinuity assumption, that these guys aren't equal. Now, using this regression discontinuity assumption, we're going to compare units just above and below the cutoff. So let's look at a y when Z is just slightly above the cutoff, and compare it to a y when Z is just slightly below the cutoff. And now, let's let y1 minus y0 be beta. And let's rewrite the expectation of y when z is just slightly above the cutoff. And now we can rewrite it using this beta I, where z is just slightly above the cutoff, and you get treated. And then that's times the probability that you get treated given that z is above the cutoff, plus the expectation of y0 when z is above the cutoff. So that's how that whole thing reduces. And of course, that's what we're actually going to see. We're going to actually see expected value of y given z is z0 plus epsilon. So we've now broken that down. And you notice this probability m of z equals 1 when z equals z0 plus epsilon. So for a sharp design, that's just going to be 1. But for fuzzy design, that'll be something less than 1. And we can decompose similarly right below the cutoff. We just decomposed that. And then if we take the difference, remember that's something we can in theory see, that actual difference on the left side, but now we're going to express it in terms of the treatment effect. So we've got the expectation of the treatment effect when z is actually slightly above the cutoff and you receive treatment times its probability, plus the expected value of the treatment effect when z is slightly below the cutoff and you receive treatment. Okay, so that makes a lot of sense, right? Plus the expected value of the y0. Okay, that's when you don't receive treatment, of course. And we're comparing the y0s at slightly above the cutoff and slightly below the cutoff. Now, this decomposition is very important. So now we want to take the limits as the epsilon tends to 0. So you remember that we thought that the units, that the intuition going way back when, was that units just to the left and right of the cutoff would have similar outcomes in the absence of treatment because they're starting out similar. So then we're going to make a continuity assumption, which is the limit from the left, i.e. as you approach z0 from below, is equal to the limit from the right of the expectation of y0 as you approach from the right. So as you go up and as you go down, the limit's the same. Okay, so which is, of course, you remember from elementary calculus is continuity. So the regression discontinuity is in the probability of treatment at below and above the cutoff. But before the treatment, you think, okay, the units at the cutoff, right to the right and right to the left of the cutoff, are quite similar. And that's what motivates this continuity assumption. Okay, a little more of this. So for the terms in this equation involving beta I, those first two, note that if the treatment effects are constant, beta I is equal to beta for all I, beta can be pulled out of the expectation. It's then identified, and it's equal to the difference in y plus minus y minus, which is y plus is the limit above, and y minus is the limit below as you approach z0. And similarly, m plus and m minus are the limits from above and below as you approach z0 in the probability of being treated. So the constant effect assumption is very strong, but it is worth noting that the result above is obtained without assuming treatment is unconfounded, and that's true in the sharp or the fuzzy design. In the sharp design, m plus minus m minus is just 1. But in the more interesting and realistic case where the treatment effects are heterogeneous, now we're going to have to make some assumptions about unconfoundedness. So let's assume unconfoundedness, by which we mean here that y1 minus y0 is independent of the treatment you receive given your score. So if we assume something like that, then you look at the next equation. Basically, we can take the m out of the expectation of beta I. Then, again, it would be reasonable to assume that the expectation of beta I given z equals z is continuous at z0. And under this assumption, the previous continuity assumption, and the regression discontinuity assumption, and the unconfoundedness assumption, then the expectation of the treatment effect at the value z0 is identified, and it's equal to, again, y plus minus y minus divided by m plus minus m minus. can see that this M plus minus M minus is kind of what's very similar to the effect of treatment assignment on the mediator when we discussed IVs and stuff. And of course, like there, it has to be greater than 0 or less than 0. But in general, it'll be greater than 0 in this context. But, it can't be 0. That's the point. It has an effect. Finally, I want to take up the case where Z plays the role of an instrument. And here, again, unlike the case we studied earlier, which led to the case, the instrument is continuous. Now, using the continuity assumption, the regression discontinuity assumption, that's about the M's, remember, right below and above the cutoff. And the continuity assumption is about the Y0s right below and above the cutoff. And the unconfoundedness assumption below, which is similar to the unconfoundedness assumption in the Angrist et al. Article. And we want to make the additional monotonicity assumption in a neighborhood of Z0, which is similar to the monotonicity assumption that they made in Angrist et al. Hahn and his co-authors show that Y plus minus Y minus over M plus minus M minus is the complier average causal effect at the cutoff Z0. So that it's the ATE for subjects who would not take treatment at Z0 minus epsilon, but who would take treatment at Z0 plus epsilon. Now, the rest of the Hahn paper is about estimation. How would you estimate this? And they talk about using a locally linear non-parametric regression estimators. Now readers who want to take that next step and are interested in estimation, they should consult the Hahn et al. Paper or the more recent literature on this topic. Now we're going to switch gears and take up the topic of longitudinal causal inference, in which a sequence of treatments is applied over time, and one wants to compare the effect of different sequences on outcomes of interest. It is a very important generalization, and it's due primarily to the work of James Robbins and his collaborators. Now, much of the work is fairly technical and difficult, and I don't intend to do a whole lot more than give a brief introduction to the topic. And as I say, it's more difficult. Other places you might look at is there's a recent book by Hernan and Robbins, and there's a chapter by Hernan and Robbins in 2009, and both of these provide a more extended yet somewhat accessible introduction, especially the book. And the book provides some intuition as well. And both provide references to the literature. Okay, so let me start with a few examples. So in neuroimaging research, measurements of neural activity are taken at periods t equals 1 through t. Okay, during each period, a stimulus Z may or may not be given. Another example, a medical researcher may wish to test if a medicine Z with nasty side effects administered every day T yields better outcomes Y than administering the medication every other day. Or the researcher might want to know if administering a medication only days when a patient's symptoms were worse than those of the previous day produces the same outcome the day after as versus administering the medication every day. You can see that last one's a little more complicated. Similarly, a company that sends its clients promotional material might want to know whether more frequent mailings are more effective than less frequent mailings. Okay, so those are a few motivating examples, and in order to keep the notation manageable, I'm going to get rid of the subscript I and simply refer to an arbitrary subject. Okay, so let's observe a subject at periods t equals 1 through t. Okay, and let's let ZT be one if the subject is assigned to the treatment in period t and 0 otherwise. And let's put an overbar to denote the cumulative sequence up through period capital T, and that's the assigned treatment regimen. And let's let ZT with the little t be the subregimen consisting of assignments through period t. Now this ZT, the big T, is one of the possible regimens. Now I've indexed them little zt because now I'm going to index all its members in some set of interest. And of course this set of interest, omega z, is a subset of the Cartesian product 0, 1 to the t. Okay, so let's let y indexed by little t of the treatment regimen zt, the whole regimen, measured at the end of period t, denote the potential outcome under the treatment regimen, little zt, and we're going to assume this depends only on treatments administered prior to the time of measurement. Pretty sensible most of the time, almost all of the time. And so here we'll hereafter write this as ytz with the little t instead of the big T. So there are many estimates we might be interested in, and we shall focus on the case where y is continuous and interest resides in averages of unit differences, which I've written, and we could have other metrics for measuring average effects, but that's what we're going to do here. So for the next several lessons, for each t, we're going to consider the average effective treatment regimen zt versus zt star, given some covariates x1 that are observed prior to period 1 treatment. That's the estimand, okay, and the average effect, which we get by marginalizing out x1. And we'll generally be interested in doing this at each time point t, although sometimes you may just be interested in it at the very end of study, in which case you wouldn't look at all of these. So in neuroimaging research, subjects are sometimes randomly assigned to treatment regimens to ascertain whether the same outcomes can be attained when patients are given medication every day versus every other day. The researcher might randomly assign half the subjects to receive daily treatment and half to receive the treatment every other day. So, in both these cases, neuroimaging and the medication case, no issues arise that we have not already addressed. But in the case where the administration of the medication on day T depends on day T symptoms, and the subsequent outcomes, such as YTZT, also depend on day T symptoms, day T symptoms are a confounder, and it is necessary to adjust for these. But at the same time, day T symptoms are an outcome of previous assignments and symptoms, and adjusting for such intermediate outcomes will generally create comparisons that are not causal, as we saw before. So fortunately, it's possible to extend the unconfoundedness conditions developed in Part 1 to cover time-varying confounding. So we'll let xt denote measurements of the time-varying confounders taken in period t, and these may or may not include the previous outcome yt minus 1 in period t minus 1, or for that matter, even several previous outcomes. We're going to assume that in each period t, measurements xt are first recorded, then treatment zt is given, followed by measurement of yt. It's important to keep that in mind. So now we're going to write the cumulative history up to time little t by putting a bar over the x. The identification conditions extend the assumption, remember Rosenbaum and Rubin, of strongly ignorable treatment assignment given covariates, that we studied in Part 1. Okay, so the potential outcomes are independent of treatment assignment given the covariates, and 0 is less than the probability of treatment given x1 is less than 1. That's the so-called positivity condition. Okay, at each value of x1, you can have both treated and untreated subjects. Now, specifically, we're going to assume, see Robbins and Hernan, for example, that for all regimens of interest, and for all values of the covariates, and for all t, we're going to make the following assumption, that potential outcomes after time little t are independent of treatment assignment at time little t, given the complete history of the past. And we're going to make this positivity condition, okay? Which is the analog of the positivity condition in the case where there's just one assignment. Or, we can think of the special case above as when zt is just z1. So, the first condition is often referred to as sequential randomization or conditional exchangeability, and the second is the positivity condition. Okay, now, under these conditions, the distributions of the potential outcomes, both within covariates, and of course, once we have that, we marginalize over x1. So these distributions are identified. So, for example, if the probability function of f is discrete, this is the formula we get. I'm going to explain a little bit about that in a moment. Okay, where f of x1 given x0 and z0 is just by definition f of x1, because that's where things start. x1 is prior to treatment assignment, and there is no x0. Now, if the probability function is identified, of course, the conditional expectation is identified as well, as below. Now, Robbins and Hernan call this result the G formula, and it is not difficult to establish and is evident from the following derivation for the case t equals 2. And then you should follow this, and then you can go ahead and extend it to t equals 3, etc. Make sure that you understand. Now we're writing on the left-hand side the potential outcomes. We're assuming covariates are discrete. Okay, so the first thing we want to do is, you'll see the first equation, and that's just the law of total probability, which you know. And then the second equation, we can stick the z1 in there. That's the only difference. We can stick the z1 in there by the unconfoundedness assumption. And then the third equation, now we're going to stick in x2 and go over the distribution of x2 given x1 and z1. Okay, again, just law of total probability, essentially. And we still have the rest. Okay, and now in the next line, because of ignorability, we can stick in the z2. And so now we have our formula, and the last line follows because if we see z1 and z2, that's a y, and that's the same y2 that we would see when z1, z2, x1, and x2 are set to those values. And so that gives us our identification condition, because now the last line we have everything written in terms of observables. To use the G formula to compare different regimens and subregimens, it is then necessary to estimate those expectations above. So then we have to estimate the conditional expectation of yt given zt and xt, and we also, of course, need to estimate those probability functions in the previous slide. So that can get tricky because this can, misspecification will generally lead to biased estimates. And as t increases, one might expect such things to become more likely because you're growing the number of things you have to estimate. And additionally, as t increases, the number of sequences also grows exponentially. In light of that latter thing, exponential growth, Robbins, Greenland, and Shu in 1999 analyzed data from an observational study of 167 children who were observed over 30 days. Now, on each day, a child may be ill or not, which is the outcome, and the mother may be experiencing stress or not, which is the treatment. So there are 2 to the 30 possible treatment regimens. Robbins and Renan also point out a problem that they call the null paradox of G estimation. Briefly, under general conditions, using parametric models to compare the means under different regimens can lead to falsely rejecting the null hypothesis of no effect, even when it's true. And this is one reason the G formula has been less used in marginal structural models, the topic I'm going to take up now. Another reason is that only recently has commercial software in SAS become available for implementing this approach. So now let's take up the topic of marginal structural models, which are based on an extension of the weighting approach in Causal Inference 1 that I presented. Okay, these models are called marginal because they are models for the marginal means, or the marginal means given a set of covariates, pretreatment covariates, and they are structural because they are models for the potential outcomes, for example, the model below. So, now, let's recall from Causal Inference 1 that when treatment assignment Z is strongly ignorable given covariates, that this weighting formula gives you the expected value of y1, and similarly we can get the expected value of y0 using this weighting approach. The weighting approach, essentially what it's doing is adjusting the distribution of the covariates to be the same among treated and untreated units. Because after all, our idea is that everybody could get treatment or everybody could get not treatment, okay? Which is basically what this says. Intuitively, a subject in the treatment group with covariates x1 and probability 0.1 of treatment, that subject represents 1/10 of the subjects in the population with those covariates. So we need to up them by a factor of 10. And then units in the control group have probability 0.9, and therefore we only have to up them by 10/9, okay? In this way, in the treatment group, the 1 unit with covariates x1 now represents 10 units, and the 9 units with covariate x1 also represent 10 units. So weighting is used to create a pseudopopulation in which both treated and control subjects have the same distribution of the covariates. Now, if we average the weighted outcomes in the pseudopopulation treatment group, then we'll get expected value of y1, and averaging the weighted outcomes in the control group gives expected value of y0. Okay, so, of course, in practice, we do not observe the population, and in addition, in an observational study, the assignment probabilities are not known, and we have to estimate them. And we want to remember that if the model for the probabilities is misspecified, this will generally lead to biased estimates of treatment effects. Now, for continuous outcome y, we can compute estimates of E of y1 and E of y0 using weighted least squares regression, where the units with z equals 1, that is, the treated units, are weighted inversely to the estimated probability of treatment given the covariates, and the units that are not treated are weighted inversely to 1 minus this probability. And then to take into account the fact that the weights were estimated, we can use robust standard errors. Okay? And if we had a dichotomous outcome, we might use logistic regression or probit model instead. Now, in the foregoing, we have used so-called unstabilized weights. Had we used stabilized weights, and you'll notice that we have a probability z equal 1 and a probability z equals 0 in the numerators instead, but had we used these weights and estimates thereof, we would get the same results because the model for y is saturated. Now, in the more complicated setting to which we now turn, it is usually necessary to model the outcomes using unsaturated models. Then it turns out that it's better to use the stabilized weights, as these lead to smaller confidence intervals for estimated parameters. The results above extend to the longitudinal case under the ignorability and positivity conditions. You can look at that formula and you can see that basically I'm multiplying these weights up through time t. Robbins and Herman call these weights unstabilized, and the stabilized weights are the ones where you have the additional term in the numerator. So in order to estimate the expectation of y1 at z1, this little z1, one proceeds as before, weighting inversely by an estimate of the stabilized or unstabilized weight. Now, at the next step, you want to estimate E of y2 with z1 and z2 as a treatment subregimen. And the units observed in period 2 with z1, the random variable z1 equal to little z1, and the random variable z2 equal to little z2. So you have to reweight these units so that the observations with covariates x1 and x2 have the same frequency as the observations with the same values as the covariates, but with z1 equal to z1 star and z2 equal to z2 star, etc. And as before, you need to estimate the weights, and as t increases, it will generally be necessary to model the outcome as well. For example, the structural model below. So clearly, our previous concerns about misspecification above for the case t equals 1, they apply here as well, but they apply more forcefully as the opportunities for misspecification increase because you're doing the weighting more times. I haven't done it, but you can include baseline covariates W in the marginal structural model. And then if you're going to do that, Hernan and Robbins in the book recommend using modified stabilized weights, as these lead to smaller standard errors than unstabilized weights. As both the G formula and inverse probability of treatment weighting can be used to estimate this treatment effect up through time little t, comparing subregimens ZT and ZT star, or on baseline covariates as well, but it's useful to look at the advantages and disadvantages associated with each approach. As we noted before, using the G formula will generally require modeling this expected value, the conditional expectation function for yt. And it will usually require modeling the probability functions for the covariates given prior covariates and prior treatments. So both of these can be quite challenging. Now, using IPTW requires modeling the assignment probabilities conditional on past covariates and assignments. And although it appears that IPTW does not require modeling the outcomes, remember that as t increases, the number of treatment regimens increases exponentially, and then you're also going to probably need a model for the outcomes. Now, if you have a sequentially randomized experiment, the treatment probabilities are known. Thus, using IPTW, it may only be necessary to model the outcomes, especially if t gets large. In such a situation, IPTW would be preferred, as the G formula would also require modeling the distribution of the time-varying confounders. And if there's a lot of confounders, that could be really, really difficult. But in an observational study, the assignment probabilities are unknown, and then you need to model them. And in this case, misspecification of the model for the assignment process can lead to very biased estimates, as can misspecification of the outcome model. You can have doubly robust estimators. I've referred you, if you're interested, to an article by Bang and Robbins. In an observational study, a good strategy might be to use both approaches and see if the estimates obtained agree adequately. While such an agreement doesn't actually indicate that either or both approaches have led to a good estimate, the agreement does offer some grounds for reassurance. Certainly, if you don't have agreement, then that would be a cause of concern. Now, more generally, it should also be remembered that in observational studies, as versus sequentially randomized experiments, the analysis is also predicated on the sequential randomization assumption, which isn't really testable. Marginal structural mean models can be estimated in both SAS and Stata. In the next lesson, we're going to discuss another method, so-called G-estimation, for estimating treatment effects using structural nested mean models in longitudinal causal studies. So, in contrast to the G formula in IPTW, which we use to estimate effects such as the average treatment effect of subregimen ZT versus ZT star, or the same thing condition on covariates, G estimation is used to estimate treatment effects conditional on past treatment and confounder history. So, for example, in a special way. So here we're looking at this estimand. We're looking at time t plus k. K could be 0, or it could be anywhere up through cap t minus t. And so what's happening here is you'll look at the first thing. So what's happening is that we have treatment regimen ZT, and then in the second we have ZT minus 1. And then after time t, you're always off treatment in the first one. And after time t minus 1, you're always off treatment in the second one. So these sequences are comparable, except that they can differ in time period t. And then we're going to condition on the covariates up through time t, and also treatment assignment up through time t. If you look at that guy, you're thinking at time t, in the first one, you get a treatment, and at time t, obviously in the second, y, you don't get treated. And now we're going to condition on you having value ZT in the time t. It's like a sort of similar to an effective treatment on the treated in a certain sense. We'll get more about that later. And you're conditioning on the covariates up through time t. And we're going to call that gamma tk, and we're going to call that of little xt and zt, and then this psi. Now, the gamma tk is a known function of xt and zt that depends on parameter psi, and psi star is the true value of these parameters. So in some instances, the outcome's only measured in period t, or interest resides only in the effects at the end. So for simplicity, I'm going to focus on structural nested mean models with effects defined on the difference scale. But G-estimation can be used to estimate treatment effects on other scales, for example, odds ratios. And in addition, you can have other kinds of structural models along these lines for distributions, for example, that can be defined and estimated using G-estimation. There's a nice article in Statistical Science by Van Steelen and Joffe upon which I'm going to draw very heavily, but you should see them for a more general treatment. And I warn you, this is probably the most complicated stuff we're going to see the entire course. So now, each estimand, this is the formula we previously had, is the effect in period t plus k of treatment in period t followed by no further treatment versus no treatment in period t, also followed by no further treatment, for units with covariates xt that actually followed the subregimen zt through period t. That's a much more succinct and nicer way of saying it than I said it before. But there's a lot there. So, for example, if cap t is 2 and then little t is 1, these would be the effects that are defined, and you can get them, you just plug them into the formula above. Okay? The structural nested mean models are structural because, again, they're models for potential outcomes, and they are nested because in each period, the effects are conditioned on the history prior to the current treatment. You can see that. because we're conditioning for an effect in time t. We're conditioning on covariates up through that time and treatment up through that time. So Van Steelen and Joffe describe various types of such models, including structural distribution models, structural models for survival data, etc. And they also provide a nice treatment of estimation. I'm going to follow their exposition, but only consider the most elementary issues. Okay, as I said, this topic is more difficult. It's difficult enough, you'll see, for the elementary case I'm going to follow. And actually, readers who aren't especially interested may just want to skim this section. And any reader that is very interested, say that wants to use this stuff or really learn it, well, they're just going to have to pursue the topic by consulting the Van Steelen and Joffe paper and the references therein, and also the Hernan and Robin book. But this stuff is harder. Okay, so let's just start with the case t equals 1, get some motivation there. Okay, and then z1 is 1 for treatment and z1 is 0 if not. So a structural mean model would contrast treatment with its absence amongst subjects with covariates x1. Okay, so you can see that. This is the same form as before, but just for this one case. So now the gamma star just depends on x1 and z1, and this psi star. Psi star, what do we want that to be? Okay, well, if little z1, right after the expectation is 0, well, we ought to want psi star to be 0. And psi is going to be a vector of parameters with true values psi star. So the gamma star of x1, z1, and psi star, for example, might equal psi star times z1 for the case where the effect doesn't depend on the covariates, for example. But you can see here that the structural mean model is thus a model for the effective treatment on the treated at x1 value of the covariates. So we considered this in Causal Inference 1, and recall that to identify this parameter, we only needed to assume that y10 was independent of z1 given x1, because the observed expectation for y1 conditioned on x1 and z1 was actually equal to the expectation of the potential outcome y11 given x1, so we're actually seeing what we needed. So we didn't need to make an extra identification assumption about that. So we also considered various ways to estimate this parameter, i.e. Inverse probability treatment weighting matching. So the thing is, these procedures aren't going to extend very well to the more general kinds of estimands that we're considering now. So we need to estimate these parameters. So here's how we do. We define a variable u star of psi, which is y minus this gamma star. Then it follows, you write it out by going back and looking at what gamma star is, and then conditioning on x1 and z1 equals z1. So it's going to follow that the expectation, the conditional expectation of u star or psi star, will be equal to the expectation of y0 conditioned on x1 and z1. And then, using the unconfoundedness condition, is going to give me that conditional expectation, condition on x1 and z1, is equal to the conditional expectation just on x1, right? Okay, important you see that because we're going to use that to set up an estimation scheme. Okay, so as a consequence of this, psi star can be estimated using estimating equations. So assuming a sample of size n, we set these to 0, and basically these d stars are a vector of known functions with q components, because we're going to estimate q parameters here. And I'm giving you an example. For that case we saw before where the gamma star was equal to psi star z, d would be one-dimensional, and you might take d of z1 x1 to be z1. So then d star minus x expectation would be d star minus the expectation of z1. And that should be fairly reminiscent of what we did back in Causal Inference 1. Those who aren't familiar with the estimating equations approach, you can look at the text by Bickel and Doxam on this subject. They have a nice treatment. There's certainly nice treatments other places as well. So to implement this approach, Van Steelen and Joffe point out that it's necessary to model the propensity score, which is needed, of course, for the expectation of d given z1 and x1, and also expected value of u star given x1. Okay? So we need to model the propensity score. And then in their paper, they also discuss efficient estimation and double robustness, which is more than we want to get into here. To estimate the effects, so we know we're going to use these estimating equations. Okay, so to estimate the effects more generally, in this general estimand that we started off with, the idea is to extend the treatment above. So for all time periods, you define these variables, UTK star of psi, and we define them so that in expectation, conditional expectation, they're equal to the yt plus k zt minus 1, 0, which makes sense. You can see that that extends what we just did. And then using the sequential randomization assumption, this will reduce to the expectation given xt, et cetera. And then we can use this to construct estimating equations. Okay, and Van Steelen and Joffe have further details. So far, we've been making the stable unit treatment value assumption due to Rubin. This assumption is twofold. First, there are not multiple versions of the treatment, and second, the values of a unit's potential outcomes depend only on the treatment assignment administered to that unit, not the assignments of other units. The first part could be violated if the treatment, for example, a surgical procedure, is performed by different surgeons, as a unit's outcome could depend on the surgeon. Ultimately, a judgment that there are no multiple treatments is subjective, and in many instances where this assumption is made, as in the example just given, it may be violated to some extent. The second part of the stable unit treatment value assumption is typically referred to as interference. Now, no interference is reasonable for many applications. For example, a unit's outcome under surgery will not depend on whether or not some other unit is assigned or not assigned to surgery. But this assumption is often violated in social context. As examples, Hong and Rodenbush consider the case of a student's reading scores. They assume a student's scores are affected by the assignment of the other students in his or her class, but not by the assignment of students in other classes. Sobel considers the moving to opportunity study, in which families in housing projects were randomly assigned to either receive a housing voucher to move, or a voucher plus assistance, with the requirement that the move must be to a low poverty area or to a control group receiving no assistance. The participants in the study within a housing project knew one another. Sobel points out that whether or not a unit moves to a low poverty area could depend not only on that subject's assignment, but the assignment of other subjects in the project. For example, Family A may move if the family receives a voucher plus assistance, and Family B, which is friendly with Family A, also receives a voucher plus assistance. But if Family B is assigned to the control group, Family A might not move. Hutchinson and Halloran, who I'll hereafter refer to as HH, consider the case of infectious diseases. Suppose that an individual is unvaccinated. Contrast that with the case in which all individuals with whom he is in contact are vaccinated or unvaccinated. It is easy to imagine that in the former case, he does not contract the disease, and in the latter case, he does contract the disease. In all these cases, an individual's assignment stays the same, but the assignment of other units varies, and consequently, the individual gets a different result. This has been called a spillover effect. It has also been called an indirect effect in contrast to a comparison of a unit's outcome when that unit receives treatment and does not receive treatment. But since we've been using indirect effect in another way, I will hereafter refer to such effects as spillovers. Broadly speaking, then, there are two types of effects. One, direct, by which we mean the effect on a unit when that unit is exposed to the treatment or not, said effect now possibly dependent on the assignments of other units, as in the MTO example above, where A moves to a low poverty area if B is assigned a voucher plus assistance, and does not move if not assigned a voucher plus assistance. And two, spillover, in which a unit's assignment is the same, but the assignment of other units vary, also as in the MTO example, where A receives a voucher plus assistance, and A moves if B receives a voucher plus assistance, and does not move if B does not receive a voucher plus assistance. Before formalizing these ideas in the general case, we introduce them in the simplest possible setting, a population of two-person dyads, for example, a husband and a wife, each of whom can be exposed or not to an exercise program, after which each member's cardiovascular fitness is measured. Now, it's natural to think in this context that the husband's outcome or the wife's outcome may depend not only on whether or not he or she was assigned to treatment, but the partner's assignment as well through spillover. However, we will assume that there is no interference amongst different dyads. Suppose a simple random sample of size n has been taken from a population P of dyads. The dyads are labeled J through J, capital J, and the units I equals 1, I equals 2 for wife, 1 for husband. Let Z1J equals 1 if the husband in dyad J receives treatment, and 0 otherwise, and define Z2J analogously for the wife. Now for all pairs J and J star, we assume that assignments in dyad J star do not affect outcomes in dyad J. We can then represent the potential outcomes for dyad J as Y sub ij, Z1, Z2, where I is an element of 1 or 2, I equals 1 for the husband's outcomes, and Z is 0 or 1, depending on whether or not you treat or not treat. So Z can be 0, 0, nobody gets treated in the dyad. Z can be 1, 1, everybody gets treated in the dyad, etc. Now, we denote the observed outcome Yj. Suppose that a randomized experiment is being conducted with assignment probabilities, probability Z1J equals little z1, Z2J equals little z2, etc. Okay? So we're going to define the total effect for unit I in dyad J as Yj11 minus Yj00. So that's the case where both parties in the dyad get treated and the case where neither gets treated. Now we're going to decompose the total effect as the sum of a direct effect and a spillover effect. The total effect may be decomposed as the sum of a direct effect and a spillover effect, respectively. So you see this decomposition. The first one compares both treated to the case where the husband is not treated and the wife is treated. And then it's plus the case where the husband is not treated and the wife is treated versus, no one is treated in the dyad. Okay? Now the second case is a different contrast. In the second case, the husband is treated and the wife is not, versus the case where neither is treated, and it's plus the case where both are treated minus the case where the husband is treated. Now, in general, these two decompositions will give different values for the constituent effects. So to fix ideas, let's let Y equal 1, that's the husband, so we're looking at husband outcomes, and consider the first of the two decompositions. The total effect of treating both husband and wife versus treating neither is the sum of the direct effect of treatment for the husband when the wife is also treated, and the spillover effect from treating the wife when the husband is not treated. So it's spillover onto the husband because I is 1. In the second, the total effect is the direct effect of treatment for the husband when the wife is untreated, plus the spillover onto the husband from treating the wife when he is treated. And then, now if you want to consider the wife, just interchange the words husband and wife above. Make sure you understand it. That's not a bad thing to do. Okay. So, now if we average over the husbands in the population, or the wives, we'll get average potential outcomes. And I put the dot to say that we're averaging over the dyads, J. Okay? So, if we average over Yi, I is 1, and we average over J, we're averaging over all the husbands. As we're assuming this is a randomized study, Yi dot bar, so that's the sample average amongst the husbands, in the group where both are treated. That's a consistent estimate of the expected value for the husbands under treatment of both husband and wife. And similar remarks will apply to the average values for the other potential outcomes. Thus, the average direct and spillover effects can be consistently estimated using the sample averages. All right, we now proceed to the more general case. Above, to illustrate, we use superpopulation inference. As much of the literature on interference has evolved using design-based inference, following the treatments in Sobel and HH, we use this mode of inference to introduce the general case. Now let's go ahead and formalize. So we have a population of n, capital N, sub t units, where n, which is a subset of the nt units, so the units constitute a population that's eligible to receive the treatment of interest. And now little n of the capital N units are sampled. Now, for the nt minus n ineligible units in the subpopulation, we're going to denote that with the fancy looking I, the treatment assignment is always z equals 0. Nonetheless, the outcomes of these units may be affected by the assignments of the eligible units. That is, these units may experience spillover effects, and we might be interested in such a thing. In the MTO study, researchers discussed the possibility of spillovers onto the existing residents of neighborhoods where recipients of housing vouchers might move to, but the study did not collect data on any of these units. So, for example, consider these residents of neighborhoods which were sort of low poverty areas. They weren't eligible to receive any housing voucher, but they might have been affected by movement into their neighborhoods. So we're going to index little z to be the vector of treatment assignments. And of course, the last bunch of zeros is for those that are not eligible. And we're going to denote the allocation of the unit to treatment groups in this fashion by z, the little z. So there will be many such possible allocations. So just to keep matters basic, we will just assume the case that you can get treated or not treated, simple case like that. And then, since there are capital N units that are subject to treatment, that's how many possible values of the vector z. We're going to let y sub I z be i's outcome under the allocation z. And we're going to write the allocation z with zi, that's whatever I got assigned to, be it 0 or 1. And then z minus I, that will be all the other folks. Okay? So that's how we're going to decompose that. Now, as there are 2 to the n allocations, each unit has 2 to the n potential outcomes. And the observed outcome is just written there. So now let's consider a particular allocation z of the n units in which we treat n1 units and n0 units are not treated. Then, if you have that, you can compute the mean outcome for the units that are ineligible for assignment, okay, under that allocation. I mean, of course, if you collect the data on these units, which they talked about in the MTO but didn't do, and B, the mean outcome. Now, the mean outcome would be just the average of the treated units under that particular allocation, for the treatment units. And C, the mean outcome, why not, which would be the average over the untreated folks who were eligible. These are the controls. Okay. Now, without further assumptions, any type of comparison of different type of units, like comparing these 3 means, that would be descriptive. But now, let us suppose that the observed allocation is the result of a completely randomized experiment with N1 treated units and N0 control units. And we'll let R of N0, N1, R for randomization, denote the set of all possible randomizations. And we'll let this Rn0, N1 within these 2 things denote the cardinality of the set. Now, for every I, that is for every subject that's eligible, we will let the expectation of y sub I when that subject gets allocation little zi, and now a random allocation z sub minus I for the other subjects. That will be i's expected outcome over the 2 to the n minus 1 allocations in which I is assigned treatment little zi, like I said, and the others you vary over all possible allocations. Okay? So for the ineligible folks, zi is always 0, so the expectation is taken over all 2 to the n possible allocations. Now, if I average these over the ineligibles, so you see what I'm doing is I'm averaging over all the ineligibles. I've done it for I have the one for I. Now I'm going to average over all of these guys. And that gives an average potential outcome, or the average of the potential outcomes. Okay, and for cases B and C above, which HH call individual average potential outcomes, averaging these over the eligibles give, and you see I'm averaging over the eligible units. Y sub I when First, when I isn't treated, and second, in the case when I is treated. Now I'm averaging over all the I's. Taking expectations over the randomization set, Sobel showed that these three things are unbiased for the respective expected values that we just looked at. So that would mean that y1 bar z minus y0 bar z is unbiased for the expectation over the eligibles of treatment versus not treatment over all the other possible randomizations. Now, in the MTO studies, economists and policy researchers assume that SUTFA held, in which case the estimand above, immediately above, would reduce the average treatment effect. But if the stable unit value treatment assumption doesn't hold, this expectation reflects both treatment and spillovers. Okay? To see this, it's necessary to compare the allocations with N sub 0 control units and M sub 1 treatment units with some other set of allocations. Okay? So, a natural comparison is to use a hypothetical baseline study, little o, in which no units are treated. Well, I mean, it's very natural because that's what happens before you've done the intervention. This is, as I say, a natural choice, but it doesn't really matter. If you had chosen a different baseline, the values of the treatment and spillover effects would change, but it's no big deal. The point is to see what happens when you need to compare with some hypothetical baseline. And Rosenbaum, I might point out, uses a similar idea, that of a uniformity trial. So let's let yi little 0 denote i's outcome in this study, and let's let the expectation of y little I 0 and the expectation over I of y 0 denote the average values of the outcome for the eligibles and ineligibles, respectively, in this study. Then, Sobel showed that if you take the expectation over the randomization set, you'll get the sum of these two terms, and the second term on the right side compares the average potential outcomes of the eligible units when they are not treated with the average potential outcomes of the units in the baseline study where no units are treated. And this is a pure spillover effect. Now, the first term then is just the average effect of treatment. So if the spillover is 0, the same result would be obtained if the stable unit treatment value assumption were assumed. Otherwise, this is not the case. And an important point to note is that if you actually look at this estimand and you inappropriately think that SUTFA holds, it could be the case that the intervention is actually harmful, but you might end up thinking that it's helpful. I mean, that could happen. It could be harmful for every single unit, but you end up thinking, oh, the intervention's really great. Now, the results are obtained without making any assumptions about the nature of interference between the units, and they're useful in a cautionary sort of way, but they're not so useful for inference, as we only see outcomes in the one study that has actually been conducted. So, further progress is going to hinge on the investigator's ability to make reasonable assumptions about the pattern of interference in special cases. For example, units are grouped into strata with interference within, but not across strata, as in schools. When all the units in a stratum are given the same treatment, this is, of course, the cluster randomized experiment, which is a very familiar type of quantity, goes way back when. Now, more generally, the reader may have noticed that the results above depend on the relative proportion of treatment and control units, because that's the randomization set, and one might expect in many social contexts that spillovers are larger when a greater proportion of interfering units are treated. Now, in these cases, you can assume there is interference, but that it is limited or partial. That's an example of partial interference, what Sobel called partial interference. Now, Hong and Rodenbush, in their study of the effects of retention policies in school, use both types of assumptions, okay? One about the proportion and one about the partial interference, limited interference. HH also take up the special case where both types of assumptions apply. First, they group the N units into clusters that are presumed to be non-interfering. There's NJ units in each cluster. Now, they're going to let little zij, so that's when the ith one, in the ith cluster, the jth unit, and then the others, have some other fixed set of treatments. Okay, now that's going to denote the potential response of unit I in cluster J when I receive this treatment and the remaining units receive this other treatment. Now, we can break that down, decompose it into unit ij gets treated versus unit ij doesn't get treated, but you'll notice that we're looking at the other units are under different allocations, right, of the other units, z minus ij and z minus ij star. Now, so we break that down as in the first decomposition, and that's a direct effect of treatment for unit I in cluster J when the remaining units are allocated to this z minus ij, and the spillover comparing z minus ij with z star minus ij allocation for unit I when it's untreated. Now, as in the case when we studied mediation, and even before when we studied this for interference for the dyads, the decomposition isn't unique, okay? And now I've just written it in a second sort of way. So which one would we prefer? Well, I mean, it should depend on the substance, but oftentimes one wants to know how the units that are untreated are affected by treated units, in which case the first decomposition is more natural. So when ij gets treated, and then the others are this little z minus ij, and a 0, that's ij doesn't get treated, and z star minus ij. When they belong to the same randomization set, and these allocations are held fixed, averaging over the units in the two allocations gives the average direct effect of treatment in the allocation z minus ij, and the average spillover for the pair zij and z star minus ij. That's when zij has, maybe it's treated, and then you're in the other allocation with zi star minus ij, or 0 and whatever. Now, if instead we fix unit I, and the average of the decomposition is taken over the randomization set, you'll obtain the average effect of treatment for unit I in cluster J, but the spillover effect is going to be 0. Averages out. Thus, in HH, the allocation Zij belongs to the randomization set psi, and the other allocation Z minus Ij star to a randomization set they call phi. So averaging the decomposition over psi and phi for a fixed unit I in cluster J, that will give you the unit average direct effect over psi and the unit average spillover for the pair psi-phi. Averaging these over the units in cluster J then gives the average direct effects in cluster J over psi and the average spillover in cluster J for the pair psi and phi. And you might also average these over clusters to give the population average direct effects over psi and the spillover effects for the pair psi and phi. I know that's a lot to parse. You just have to look at it and write some of this stuff out for yourself. Now, a notable feature in HH is their consideration of standard errors of estimates. The problem is non-trivial using randomization-based inference because within each cluster a single systematic sample is taken. So then you need to make additional assumptions to obtain variance estimates, and I've referred to this elementary sampling text by Lohr. This is all well known that you have to do that. Well, to that end, HH uses a strong version of the assumption that a unit's potential outcomes depend only on the proportion of the units receiving treatment. So, specifically, suppose that in cluster J, K sub J of the units receive treatment. So what HH assumes is that for every value of Kj, a unit's potential outcomes depend only on whether the unit receives treatment or not. In other words, within allocations where K sub J units are treated, the stable unit treatment value assumption holds. Now, HH called this assumption stratified interference, and the assumption is proved important in the subsequent literature on interference in terms of making headway and getting some standard errors. Now, under the stratified interference assumption, and the assumption that treatment effects are additive, i.e. the same for all units, HH derived unbiased variance estimators for various direct and spillover effects. Now, if the treatment effects are heterogeneous, the estimators are conservative, which, if you recall from Causal Inference 1, this is essentially reminiscent of the variance estimators for the average treatment effect we studied there. The same kind of thing happened. It is worth pointing out, however, that The stratified interference assumption is quite strong, as of course is the additivity assumption, which oftentimes one doesn't believe, but okay, we can live with conservative estimate. But that said, the stratified interference assumption is very strong because it basically says, okay, if you treat kj units, then what happens to unit I doesn't vary as you treat any set of kj within the cluster. So let me give you an example. In the MTO study, if unit I moves, only if unit I prime is also assigned to the treatment group and moves, then for kj greater than or equal to 2, the stratified interference assumption cannot hold. So you can see that for yourself. Just think about it a moment. So now more recent work on interference takes off from the starting points above that I've sort of given. The reviews by Hong and Vanderweel contain references to some of this work. We close by taking up a seemingly ingenious idea that, to the best of my knowledge, originated in econometrics literature, and which is found and continues to find widespread use in the social sciences for the analysis of observational studies. So far, we have assumed that treatment assignment is unconfounded given measured covariates. Now, as we know, in many instances, this assumption is not reasonable. Now, economists argued that if measurements were taken on multiple units in a cluster, and all these units shared a common unobserved variable u, then u, even though it is not measured, could be taken into account using standard models such as regression. For example, let's have panel data, or repeated measures data, statisticians might call it, longitudinal data, statisticians might also call it. Individuals are observed at multiple points in time. So, here, each individual is a cluster, and U measures unobserved variables that are unobserved and constant over time. To fix ideas is one example. Economists have used such data to study the effect of marriage on men's earnings. They've been doing this for more than 50 years. The question here is whether more productive men are more likely to be married or whether marriage increases productivity. Now, here, measured covariates have included such things as education, family background, occupation, industry, union status, etc. But productivity itself is not measured. Suppose then that U represents unmeasured aspects of productivity and U is constant within units. Now, let's also suppose that earnings are some transformation of earnings such as the natural log. Let's call that yt. And we have unit I equals 1 through n. That's the cluster. And the cluster is observed in period t equals 1 through capital T. It has to be more than 2, greater than at least 2. And let's say that that depends on time-varying regressors, which will denote xit. Marital status is zit in period t, 1 if you're currently married, 0 otherwise. And ui, which you'll notice is constant over time. There's no t on it. And random errors epsilon it, or usual regression types of errors. Now, to keep matters simple, and to mirror the empirical literature, I just want to consider perhaps the simplest case, linear regression, etc. So let's let yt have this linear regression form, and zit with the bar over it will be the set of treatment allocations, or treatment assignments rather, from time 1 through time t, little t. And we're going to make one of two assumptions. First of all, either the epsilon sub it, the regression error, given the complete history of the covariates x, the complete treatment assignment z, and the unobservable variable is 0. Now, this is an assumption that Chamberlain, who's written about this stuff, called strict exogeneity. And then there's a weaker assumption called sequential exogeneity. And this just requires that the epsilon it up through time little t, the history of the covariates up through time little t, and the treatment assignment up through time little t and u are 0. The strict exogeneity assumption is unreasonable. You can see it for yourself. If xit were to contain lag values of y, which it could, and in this case, you better off assuming sequential exogeneity because the other is just unreasonable. Now, there's a couple of ways we could treat UI. If UI is treated as a mean zero random variable that's independent of xit and zit, then we obtain a random effects model. But the random effects model is often unreasonable. For example, in the marriage example, it would not be reasonable to assume that unmeasured aspects of productivity are independent of education and other covariates. So for that reason, economists often prefer to treat UI as a so-called fixed effect. And I've cited Munlock, who had the first insight into this. In this case, by including dummy variables for each cluster, UI can be treated as a parameter to be estimated up above. Well, some identification conditions, but nothing substantial. Or it can be differenced out in several ways. You can difference out from Y1, and you see that when you difference it out, there's no UI. Or if you took the mean, instead of Y1 above, you just took the mean Y bar over all the time points within the ith cluster, you'll see again when you do the arithmetic that the UI pops out. Now, if you have strict exogeneity, consistent estimates of beta and tau, the so-called treatment effect, we're going to call it a treatment effect for now. It's not really a treatment effect, we'll see, but the purported treatment effect. Anyways, you can get these consistent estimates using ordinary least squares. And typically, this purported treatment effect has this very simple form of tau times ZIT. So if ZIT is 1, you're adding tau, and if ZIT is 0, nothing. And the estimate tau hat is simply, in this case, interpreted as an effect, and the exact nature of which is not stated. Not surprising, because one starts with the model and never says what the estimand is. We'll see more on that later. Estimation is more complicated under sequential exogeneity, and I won't be discussing that here. You can see the book by Wooldridge for greater coverage of this and other topics for fixed effect panel data models. Okay? All right. To discuss that would be a real distraction. It's more complicated, and the point I want to make here is more about identification, less about estimation. So, now, throughout this course, we've emphasized the importance of using potential outcomes to define unit and average effects, then stating conditions under which these are identified, then, and only then, comes estimation. Okay? So, in the approach above, the regression model is simply put out there, and this parameter, tau, which is a byproduct of the model, is simply interpreted as a treatment effect. As I said already, this approach is problematic. Following paper I wrote, we're going to reformulate this problem within the framework of longitudinal causal inference, which we studied in Module 10, using potential outcomes. So in each period t, we're going to assume that time-varying covariates are first observed, then treatment, then the response. An important point of great consequence, not considered at all in the prior approach, the regression approach I just talked about, is the dependence of the time-varying covariates on prior treatment assignments. So, I'm going to need to set up and define some time-varying covariates, and you'll notice that the time-varying covariates can depend upon the prior treatment assignments. Not just the potential responses, the YT-ZT, but the time-varying covariates as well. This is an important point. We're going to see why in a moment. Analogously with the regression model previously considered, which I've written up again, let's look at a so-called causal model. And you'll see that the causal model looks very much like the regression model, except that now the dependence of the covariates on the prior treatments assignment is made explicit. And second, the parameters appear with the C to denote that this is a causal model, or model for potential outcomes, or what Robbins might have called a structural model. So, for I equals 1 through n, and for all the time points t up through t, I'm going to make assumptions that are analogous to the assumptions we made about strict exogeneity and sequential exogeneity, so that we can study when these might hold, and when the causal model might give the same results as the regression model. That's the point, after all, to ask, does a regression model work, and if so, how? We write the parameters with the C to distinguish these from the regression model. Okay, and in general, we know that the two sets of parameters are not going to be identical. So we're going to have assumptions that are analogous to strict exogeneity and sequential exogeneity. So you'll notice that in the first, we condition on the complete set of covariates, and in the second, we condition on the set of covariates up to time little t for the error. So in the first, little t is less than big T in general, but in the second, they're the same. Now, under either assumption, the expectation comparing treatment sequence z little t with z star little t, remember that's what we do when we do longitudinal causal inference. Those are the things we compare, or we compare it within covariate classes. At least that's one of the things we do. Anyways, we can write that as follows. So you'll see that what happens is we have this stuff about the treatment assignment, z's, back there, the last two terms, and we have the business about the time-varying covariates. Okay, so in general, those covariates are going to be different under those two subregimens, ZT and ZT star. And so the comparison between the different treatment subregimens, it depends not only on these tau terms, but also on the effects of the different treatment histories on the time-varying confounders, which seems to be completely lost in this literature. Now, to estimate the effect of little zt versus zt star, no matter what procedure is used to estimate the parameters, then we see that it's necessary to model the effect of the treatment history on the time-varying confounders if this guy up there isn't zero, which we probably don't think it would be. So now, if we look at that last term, the tau c's with the zt and zt star, two different assignments, that guy is the effect of the two different subregimens, comparison of these, only if the other guy is zero. So how would that happen? Well, one thing we might assume is that treatment doesn't affect the time-varying confounders. Well, that assumption is pretty unreasonable in most cases of interest. Okay, so we don't want to assume that. That'd be kind of a little crazy. So thus, we might focus on those assignments where the covariates are the same under the two things, but we need to focus on such assignments. But when might that occur? That might occur when the two assignments are the same, and then at time t, you're just comparing treatment versus zt star is zero. Okay, so then the time-varying covariates would be the same up through period t minus 1 under the two different treatment subregimens. And we might make tau c of zt bar equal to just tau c times zt. That's, so then the effect would be tau c. If you got, it would be tau c, right? So that would allow you to compare a whole set of treatment assignments or treatment subregimens, if that model were true, all treatment subregimens that agree up through time t minus 1. Now, I'm not sure, but presumably that might be what empirical researchers are attempting to estimate when they take tau of the observed treatment assignment, in the regression model, it would be tau times ZIT. Okay, so I've given conditions under which consistent estimates of the tau c parameters can be obtained using the regression model. And of course, we're going to not even try to deal with the time-varying covariates because that just adds additional layers of complexity on top of this all. You'd have to model them, et cetera, et cetera. So we're going to just take the case where the time-varying covariates, where they're the same up through the first t minus 1 periods. And that can happen, like I say, the z's are the same up through the first t minus 1 periods, or we might have some model in which the number of treated times during the first t minus 1 periods are the same in the two, and the outcome only depends upon the number of times the treatment is obtained in the first t minus 1 turns. But we're going to just assume that that's the case, that we're under some model or some setup in which that's reasonable. And now I'm going to talk about using the regression model. And if we assume sequential exogeneity, which is, remember, the weaker of the two assumptions, exogeneity assumptions, I need to make a sequential randomization assumption to justify within this longitudinal causal inference framework using the regression. Okay, so now in the module on longitudinal causal inference, what did we assume? We assumed that period t treatment assignment was independent of future potential outcomes, given the previous outcomes, confounders, and treatment history. Now, to make this work here, we have to assume a little stronger. We assume that period T treatment assignment is independent of future potential outcomes and potential confounders as well, given the previous outcomes confounders, treatment history, and the unobserved confounder U. So this is a little different and, of course, a bit stronger than the sequential randomization assumption we assumed in the module on longitudinal causal inference. Okay, now that said, the vast majority of analyses using fixed effects models use OLS regression, which gives consistent estimates of the model parameters under the model and under strict exogeneity, not under sequential exogeneity. So here, of course, the identification conditions required to justify using OLS would be even stronger, right? Because remember, that's a much stronger condition. Okay, now what we require is conditional independence of future potential outcomes and the complete assignment history of the ZIT. So in observational studies, an assumption like this is almost never credible because it requires that potential outcomes do not affect subsequent treatment assignments, among other things. So it's just simply, I'm hard-pressed to imagine any situations in which I'd really believe this in an observational study. That's my take on fixed effects models for longitudinal data. But remember, you have these fixed effects models whenever you have clustering. You can have, random effects models or fixed effects models whenever you have clustering. And so clustering arises not only in the longitudinal case, but we've also seen it arises frequently in schools, dyads, families, husband-wife pairs, neighborhoods, etc., etc. So economists will often use fixed effects models for the cluster in this case. And in this case, the fixed effect is postulated to account for a common environment within the cluster that is not measured by observed variables. For example, within a family, if you're looking at the siblings and you're trying to model their education, there's maybe some latent family environment about unmeasured variables, which might be books in the household. It might be the parental attitudes toward education, these kinds of things, whether parents encourage the kids to be creative thinkers, that sort of stuff. Anyways, that kind of stuff that isn't really picked up by the observed covariates. Now, if you have something like that, the problems above won't arise because we're not in this longitudinal case. But there's another problem. When you assume the stable unit treatment value assumption, here the problem is it's likely that the units within a cluster interfere with one another. So even if you had conducted a randomized experiment, ignoring interference would lead to invalid inferences, as we saw previously in the lessons on interference. Second, in our treatment of interference, the estimates we considered were identified under randomization conditions. Now, as the rationale for using fixed effects models is to control for unmeasured confounding in observational studies, different kinds of identification conditions would need to be developed. And I'm saying that further development of this topic would be useful. In fact, I'm working on it. Maybe stay tuned. Well, this concludes Causal Inference 2, and thanks for making it through these two courses. So to wrap up Causal Inference 2, I guess what I'd want to say about it is, well, we've gone far beyond the material in Causal Inference 1, where we focused on average treatment effects and effective treatment on the treated. The estimands we've considered here in Causal Inference 2 are more complicated, and with that, you really tend to get more complicated identification conditions and more complicated estimation procedures. And I think it's, useful to note that the more complicated identification conditions, well, you're trying to do something more, but you have to make more assumptions. And if these assumptions aren't reasonable, your results aren't going to be reasonable. And so it's very nice to know what kinds of assumptions you need to make, but it might make you want to say, okay, I know these assumptions aren't reasonable, so I'm not going to put much faith in my estimates, or I'm just not going to do that. So the statistical literature is very useful because it really lays out nice and clean what you need to assume in order to do these kinds of things. And folks might not always like it, but it also tells you what you shouldn't be doing and what you shouldn't believe sometimes. And so I think that's very, very useful to know. All right, well, The other thing I want to say is that I know causal inference too has been more complicated, and there's so much. I've just tried to skim the surface of it and give you some of the kinds of the main topics and the sorts of main ideas behind these. But I try to give you references so that you can go and if you're really interested in something here or a particular thing, that you can go and read on your own now. Okay, well, thanks again.